The most dangerous version of the asteroid skeleton story is not that it is false. It is that the false story stands in front of something real, something quieter, older, and almost as unsettling. No human skeleton was found inside Bennu. No NASA team opened an asteroid sample and discovered bones folded into ancient rock. No skull was lifted from black dust. No fossilized hand reached back from a time before Earth. That image belongs to science fiction, and as science fiction, it has power. It breaks time in a single glance. It asks us to imagine a human body sealed inside material from the early solar system, as if our species had somehow existed before the planet that made us up. But that is exactly where the claim collapses. A human skeleton cannot be older than Earth. The Smithsonian Human Origins Program describes fossils from Jebel Irhoud, Morocco, dating to about 300,000 years ago, as among the oldest known Homo sapiens fossils. That is a deep human age. It reaches far beyond written history, beyond agriculture, beyond cities, beyond every language now spoken on Earth. But next to Bennu, it is almost yesterday. NASA describes Bennu's sample in the context of a roughly 4.5 billion-year-old asteroid, material tied to the earliest chapters of the solar system. That is not the age of a civilization. It is not the age of a body. It is the age of dust, minerals, heat, water, impacts, and chemistry, before Earth became the world we know. So the skeleton claim does not merely get a detail wrong. It forces two timelines together that science keeps apart. Homo sapiens belongs to the recent surface of Earth's story. Bennu belongs to the dark chemical archive from which planets formed. And yet, the real discovery is not small. On September 24, 2023, a capsule fell into the Utah desert with no bones inside. It carried no alien remains, no preserved astronaut from a forgotten epoch, no fossilized warning from a civilization erased before our planet cooled. What it carried was 121.6 grams of material from asteroid Bennu, protected for laboratory study after a long journey by NASA's OSIRIS-REx mission. Inside that material, scientists did not find anatomy. They found chemistry. They found high carbon content and evidence of water-bearing minerals. Later reporting described hydrated minerals, clay minerals, sodium-rich salts, carbonates, sulfates, chlorides, fluorides, amino acids, amines, formaldehyde, carboxylic acids, polycyclic aromatic hydrocarbons, N-heterocycles, nucleobases, and sugars. NASA also reported stardust and interstellar organic material in Bennu samples, meaning that some grains or components may predate the solar system itself. That is the stranger truth hidden behind the fake skeleton. Not a body older than Earth, but a chemical toolkit drifting through space before life appeared here. The difference matters. A skeleton would be evidence of an organism. Bones would mean development, tissue, metabolism, ancestry, death. A human skeleton would mean the entire story of human evolution had been shattered beyond recognition. It would demand not a revision, but a collapse of biology, geology, planetary history, and time. That is not what the Bennu sample shows. The Bennu sample shows something more subtle and more scientifically useful: prebiotic chemistry. It contains ingredients associated with life on Earth, but not life itself. Amino acids are used by living organisms to make proteins, but amino acids alone are not organisms. Nucleobases are used by terrestrial life to store and transmit genetic information in DNA and RNA, but nucleobases alone are not a message from a cell. Sugars can be part of biological molecules, but their presence in an asteroid sample is not proof that anything ever lived there. This is the line that must stay clear. Life-related chemistry is not life. Organic molecules are not fossils. Carbon is not a corpse. Water-altered minerals are not an ocean with creatures swimming in it. A chemical environment where ingredients can interact is not a living world. But it is still profound. Because if Bennu preserves material from the early solar system, and if that material contains carbon-rich compounds, water-altered minerals, salts, amino acids, nucleobases, and sugars, then scientists are not looking at a monster in a tomb. They are looking at a record of possibility. They are studying how some of the raw ingredients connected to biology may have been distributed through space before Earth became alive. That question is quieter than a skeleton, but it reaches further. It asks whether Earth's life began with ingredients made only here, or whether some of those ingredients were already traveling through the young solar system inside carbonaceous asteroid material. It asks whether impacts delivered chemistry as well as destruction. It asks whether the boundary between lifeless space and living worlds is not a wall, but a long chain of physical and chemical steps. Bennu does not answer all of that. It cannot. The presence of amino acids, nucleobases, sugars, and salts does not prove life existed on Bennu. It does not prove life exists elsewhere. It does not prove that Earth was seeded in any simple or dramatic way. But it gives scientists something rare, a clean piece of the ancient record. That is why OSIRIS-REx mattered. A spacecraft can observe an asteroid from orbit. It can map its surface, measure its shape, and study reflected light. But a returned sample can be placed into laboratories on Earth, examined by instruments too large and too sensitive to fly through space. It can be divided, preserved, compared, tested, and retested as methods improve. The scientific power is not in spectacle. It is in control. A rumor needs only an image. A mission needs years of engineering, navigation, contamination prevention, curation, and analysis. The false claim imagines a dramatic opening, a sudden revelation, a skeleton where no skeleton could be. The real story is slower. A capsule is sealed. A sample is protected. The material is handled at NASA Johnson Space Center in Houston, Texas. Teams study grains, minerals, isotopes, and molecules. The discovery unfolds not as a scream, but as a sequence of measurements. And still, the atmosphere around Bennu feels cinematic for the right reasons. Bennu is dark. It is carbon-rich. It is a near-Earth asteroid, and its material carries memory from a time when planets were still assembling. It is not a tomb, but it is an archive. It does not contain a human past older than Earth, but it may contain clues to chemical processes that helped shape the conditions from which life could later emerge. That is why the skeleton story is so tempting. It gives the asteroid a human face. It makes the ancient material emotionally legible. We understand bones. We understand death. A skeleton inside an asteroid would be a perfect symbol of cosmic horror. The familiar body, impossible in impossible time. But reality asks for a different kind of attention. Imagine no rib cage, no spine, no skull. Imagine instead black grains held in sterile containers. Imagine minerals that remember water. Imagine salts left by brines. Imagine carbon compounds assembled without biology. Imagine amino acids that are not flesh, nucleobases that are not genes, sugars that are not cells, and dust that may be older than the sun. That is not less strange. It is stranger because it does not require breaking science to feel impossible. It fits within what researchers can test, and still it points toward one of the deepest questions we can ask. How much of life's toolkit was already present in space before Earth became alive? The answer did not arrive as a skeleton. It arrived as a sealed capsule falling through the sky, descending toward a desert range near Salt Lake City, Utah, carrying a small amount of ancient Bennu material that had to be protected from the modern Earth the moment it came home. The answer did not arrive as a skeleton because it was never supposed to look like one. It arrived as a small, blunt capsule dropping out of the morning sky above Utah, carrying a kind of evidence that could be ruined by the very planet it had come to help explain. On September 24, 2023, NASA's OSIRIS-REx sample capsule returned to Earth and landed at the Department of Defense Utah Test and Training Range near Salt Lake City, Utah. After years in deep space, after contact with Bennu, after a journey that had turned a distant asteroid into something physical and recoverable, the object at the center of the story was suddenly on the ground. Not a body, not a fossil, not a secret chamber opened inside an asteroid. A capsule, small enough to seem almost ordinary, but carrying 121.6 grams of material from Bennu, or 4.29 ounces. Less than the weight of many objects we handle without thinking. Less than a cup of coffee. Less than a paperback book. And yet those grams had crossed a boundary that scientists spend entire careers trying to reach. They had been collected from a carbon-rich asteroid, sealed away from Earth as carefully as possible, and returned for study inside laboratories designed to keep the modern world from confusing the ancient record. That is where the rumor of the skeleton becomes most revealing. The false version of the story imagines discovery as spectacle, a cracked asteroid, a hidden shape, a human form where no human could be. It asks for the drama of recognition. A skull, a spine, a rib cage. Something our eyes could understand instantly. But the real sample demanded the opposite response. It required restraint, distance, clean handling, chain of custody. The truth inside the capsule was not something to be stared at in a desert wind. It was something to be protected from dust, water, breath, fingerprints, plastics, fuels, and every trace of Earth that might blur the signal from Bennu. So the Utah desert mattered not because it was the final destination, but because it was the first controlled threshold. The Department of Defense Utah Test and Training Range is a landscape made for distance. Wide open ground, restricted access, airspace, and terrain where a falling spacecraft component can be recovered without dropping into a city, an ocean, or a forest. In the cinematic version of the moment, the capsule is easy to imagine as a meteor in reverse, not an unknown object burning toward Earth, but a known messenger coming home under human watch. It entered the atmosphere, survived the heat and violence of return, and descended toward a designated range where recovery teams could reach it quickly. The story narrows there, from cosmic scale to human procedure. Because 121.6 grams of Bennu material was not valuable in the same way a gold nugget is valuable. It was valuable because of context. It mattered that the material came from Bennu. It mattered that it was collected by a spacecraft rather than found after falling through Earth's atmosphere as a meteorite. It mattered that the capsule stayed sealed. It mattered that the sample could be taken to NASA Johnson Space Center in Houston, Texas, where astromaterials can be curated and studied under conditions built around preservation. A meteorite found on the ground can still be scientifically precious, but it has already passed through fire, weather, impact, and exposure. It has already entered Earth's chemistry. Rain can touch it. Microbes can colonize it. Soil can contaminate it. Human hands can alter it. With OSIRIS-REx, the power of the mission came from a different promise. Material from Bennu could be delivered with its history less scrambled, its contact with modern Earth minimized, its ancient chemistry kept as clean as engineering and curation could make it. That is why the sealed capsule is the real central object of this chapter. It is tempting to rush past it, to treat the landing as a simple delivery scene before the science begins. But the landing is part of the science. The capsule was not merely a container. It was a barrier between two worlds. On one side was Bennu material, carbonaceous asteroid dust and fragments tied to the early solar system. On the other side was Earth, alive, wet, chemically active, filled with organic matter, filled with the very kinds of compounds scientists hoped to study in the sample. The irony is quiet, but enormous. To understand ingredients associated with life, NASA had to protect the Bennu sample from life. That single fact does more to dismantle the skeleton myth than any dramatic denial. If researchers had truly opened a capsule and found human bones, the problem would not only be evolutionary time, it would be contamination, handling, origin, chain of evidence, and every question that separates a scientific result from a story built to spread. Real astromaterials research does not begin with a shocking photograph and a claim. It begins with preserving the sample so that later measurements can be trusted. The public image of discovery often imagines a moment when someone sees the truth. A lid opens. A scientist gasps. The camera zooms in. But with Bennu, the first truth was that the material had survived the return and could be moved into the systems built to study it. The drama was not a skeleton visible in the dust. The drama was the dust itself, still sealed, still protected, still carrying clues that had not yet been fully translated. And there is something almost science fictional about that restraint. A spacecraft goes to a dark asteroid named Bennu. It touches the surface for a brief collection maneuver. It brings home grains from a body connected to the earliest history of the solar system. The capsule falls into the Utah desert, and instead of opening it like treasure hunters, scientists treat it like a message that can be damaged by impatience. The message was measured in grams. 121.6 grams. That number matters because it anchors the story in reality. Viral claims grow by becoming large, vague, and theatrical. They say skeleton, ancient human, impossible asteroid, hidden NASA discovery. The actual mission gives us something smaller and stronger, a measured mass, a return date, a landing range, a curation facility. September 24, 2023. Department of Defense, Utah Test and Training Range. Near Salt Lake City, Utah. NASA Johnson Space Center in Houston, Texas. 121.6 grams of Bennu material. The real facts do not weaken the wonder. They focus it. That sample contained matter from a place no human has walked, from an asteroid no astronaut has touched, from a small, near-Earth world that preserves chemical records older than biology. The value of the capsule was that it brought that record into reach without pretending it was something else. Not remains. Not a corpse. Not evidence that humans somehow predated Earth. The capsule carried regolith, dust, grains, and fragments whose significance would come from laboratory analysis, not from visual shock. The sealed return also changed the relationship between spacecraft and scientist. Before the capsule landed, Bennu was known through remote measurements, images, navigation data, and the spacecraft's encounter with the asteroid's surface. After the capsule landed, Bennu became a material presence on Earth. It could be divided, cataloged, preserved, and examined by instruments too heavy, too sensitive, or too complex to send across space. It could be compared, remeasured, and saved for future researchers with better tools than we have now. That is one of the quiet revolutions of sample return. A spacecraft can carry instruments outward, but a returned sample brings the asteroid inward. It lets the laboratory become part of the mission. And so the Utah landing was not an ending. It was a handoff. From flight dynamics to curation, from recovery teams to clean rooms, from a capsule in a desert to protected material at NASA Johnson Space Center, from a spacecraft's long arc through the solar system to the slower, more careful work of chemistry, mineralogy, and interpretation. The skeleton rumor wants the story to end at the opening of a container. The real story begins there. Because once the capsule was safely recovered, the most important question was no longer whether Bennu held something shaped like us. It was whether this small amount of protected asteroid material could show how worlds inherit chemistry, how water altered minerals, how carbon compounds were stored, and how the ingredients associated with life may have been distributed long before life existed on Earth. The desert scene gives us the object: a capsule on the ground, a measured sample inside, a chain of protection leading toward Houston. But the deeper reason OSIRIS-REx mattered was already present before any laboratory result was announced. The achievement was not just what the sample would later reveal. It was that the United States had brought home material from an asteroid at all, turning a distant point of ancient carbonaceous rock into something scientists could hold, protect, and study under the full power of Earth's laboratories. The desert scene gives us the object, but the mission's deeper importance begins with a change in scientific posture. Before OSIRIS-REx, Bennu could be watched, modeled, mapped, and measured from a distance. After OSIRIS-REx, Bennu could be examined as material. Not as a point of light, not as a shape reconstructed from instruments, not as a rumor dressed up as a tomb, as grains, as dust, as carbonaceous asteroid material placed inside laboratories on Earth. That shift is why the capsule mattered before anyone announced amino acids, salts, water-bearing minerals, or any other laboratory result. The achievement was already historic the moment the sample came home. NASA's OSIRIS-REx mission was the first United States mission to deliver a sample of an asteroid to Earth. The full name of the mission sounds almost like a compressed research program: Origins, Spectral Interpretation, Resource Identification, and Security Regolith Explorer. Each part of that name carries a different ambition. Origins points toward the early solar system and the chemistry that existed before Earth became the living world we know. Spectral Interpretation points toward the act of reading surfaces from afar, using light to infer what a distant body might be made of. Resource Identification suggests a practical future, where asteroids are not only scientific targets, but places whose materials may one day matter to exploration. Security reflects Bennu's status as a near-Earth asteroid, an object whose orbit makes it important to understand with care. Regolith Explorer brings the story down to the surface itself, the loose, broken, dusty material covering a small world. But the genius of OSIRIS-REx was that it did not stop at interpretation. It did not only ask what Bennu looked like through instruments. It went there, studied the asteroid closely, touched it briefly, collected part of its surface, and sent that material home. This is the essential difference between remote observation and sample return. A spacecraft can carry remarkable instruments, but every spacecraft is limited by mass, power, volume, heat, radiation, and distance. Anything launched from Earth must survive the violence of ascent, the cold and vacuum of space, and the strict engineering limits of flight. Instruments sent across the solar system have to be compact, rugged, efficient, and carefully chosen long before the mission reaches its target. A laboratory on Earth is different. It can hold instruments that are too large, too delicate, too power-hungry, or too complex to fly. It can use methods that require clean rooms, multiple preparation steps, long measurement times, and teams of specialists working across institutions. A returned sample can be analyzed, reanalyzed, preserved, divided, compared, and revisited as technology improves. It can be protected for future scientists who may have tools that do not yet exist. That is why a sample return changes the scale of what can be known. A distant asteroid can tell us many things from afar. Its brightness can hint at its surface. Its spectrum can reveal clues about minerals and organic material. Its shape can be mapped. Its rotation can be tracked. Its orbit can be calculated. A spacecraft nearby can refine all of that, turning a faint object into a detailed world. But there is still a boundary between observing a surface and holding its material under the full power of Earth's laboratories. OSIRIS-REx crossed that boundary, and that boundary matters, especially for an asteroid like Bennu. Bennu is carbon-rich. It belongs to the kind of world that scientists study because it may preserve records from the early solar system. Earth has oceans, weather, plate tectonics, biology, heat, erosion, and a long history of chemical recycling. Our planet is alive in more than one sense. It constantly changes its own evidence. Ancient material on Earth can be buried, melted, altered, dissolved, or overprinted by later events. Bennu, by contrast, offers access to a different kind of archive, dark, primitive, and comparatively less processed by the forces that remake a planet. That does not mean Bennu is a frozen museum, untouched in every way. Its parent material has its own history. Scientists infer alteration from minerals, chemistry, isotopes, and physical evidence. But even with that complexity, carbonaceous asteroid material can preserve clues that are extraordinarily difficult to isolate on Earth. It can hold records of minerals that interacted with water, carbon compounds that formed or accumulated before life, and grains that connect the sample to deep cosmic history. This is why the skeleton myth is such a poor substitute for the truth. A skeleton would reduce the asteroid to a hiding place for a body, a locked room mystery with an impossible corpse. The real mission turns Bennu into something stranger and more scientifically powerful, a carrier of material from a time when planets were forming and chemistry was being sorted across the young solar system. The returned sample also changed the confidence of the investigation. If scientists rely only on telescopes or flyby measurements, every conclusion must pass through layers of inference. What does this wavelength mean? What mixture of minerals could produce that spectral signature? How does surface texture affect the measurement? What has space weathering done to the outermost grains? These are not weaknesses in science. They are the normal questions of planetary exploration. But a returned sample lets researchers test those interpretations directly. The name spectral interpretation becomes especially important here. Before sample return, spectra are a way of reading from a distance. They are powerful, but they require calibration against known materials. A Bennu sample on Earth can help scientists understand what the spacecraft saw when it looked down at the asteroid. It can connect remote sensing to physical reality. The light measured in space can be compared with minerals, organics, and textures in the laboratory. The distant reading and the returned material can speak to each other. That is not as theatrical as a skull in an asteroid, but it is how a real cosmic signal becomes knowledge. The sample also entered a network of institutions built for careful work. NASA Johnson Space Center in Houston became central to the curation of the material. That matters because curation is not simply storage. It is protection, documentation, allocation, and preservation. The goal is to keep the asteroid material scientifically useful, to prevent avoidable contamination, and to make sure that analysis can happen not only now, but over time. The Bennu sample is not a trophy. It is evidence. And evidence from an asteroid is rare. The United States had returned samples from the Moon during Apollo, and NASA had experience with other kinds of returned space material, but OSIRIS-REx marked the first time a United States mission delivered asteroid material to Earth. That fact gave the mission historical weight even before the first published findings. The capsule did not need to contain something sensational to be extraordinary. Its existence meant that a small, near-Earth asteroid had become part of the laboratory record of Earth. This is also why the amount of material should not be judged by ordinary intuition. 121.6 grams does not sound like much if we imagine cargo, treasure, or a dramatic relic. It sounds small. But for astromaterial science, small can be immense. A few grains can be enough for high-precision measurements. Tiny fragments can reveal mineral structures, organic compounds, isotopic patterns, and textures that preserve sequences of formation and alteration. The value is not in bulk. It is in provenance, cleanliness, and context. A rock picked up from Earth has an Earth story wrapped around it. A meteorite found after falling through the atmosphere has already endured entry, impact, and exposure to the terrestrial environment. Meteorites are scientifically precious, but they arrive without the same controlled collection history. Bennu material, by contrast, came from a known asteroid, collected by a known spacecraft, sealed for return, and handled through a planned curation process. That chain of custody gives the sample a special kind of power. It allows scientists to ask more exact questions. Not simply, what is this dark extraterrestrial material? But what is this material from Bennu? How does it compare with what the spacecraft measured at Bennu? How does it compare with meteorites? How does it compare with other asteroid samples studied through international collaboration, including work connected to JAXA's Hayabusa 2 community? How does it help refine the way we interpret carbon-rich bodies across the solar system? The answers do not have to be simple to be meaningful. In fact, the difficulty is part of the reason sample return matters. Bennu's chemistry is not a single message. It is a layered record. Minerals, organics, salts, and grains may each point to different parts of the asteroid's history. Some evidence may reflect processes on Bennu's parent body. Some may reflect alteration by water. Some may preserve older cosmic material. To separate those threads, scientists need more than a camera on a spacecraft. They need laboratories, time, comparison, and instruments capable of reading matter at extremely small scales. This is where the story becomes quietly cinematic. The capsule in Utah was not the final scene. It was more like the arrival of a locked archive at the door of a library built to read it. The dramatic moment was the landing, but the deeper drama was the beginning of examination. Every protected particle carried the possibility of linking a small asteroid to vast questions: how planets formed, how water altered primitive material, how carbon chemistry spread, and how ingredients associated with life became available in the environments that preceded biology. None of that requires a hidden human past. It requires something more patient and more unsettling. It requires accepting that our origins are not only written in fossils, bones, and ancient landscapes on Earth. Part of the story may also be written in dark dust from small bodies that formed alongside the planets, preserved in places where no human ever stood. That is why OSIRIS-REx mattered before the laboratory headlines. It changed Bennu from a remote object into a returned witness. It gave scientists material that could be studied with the best tools on Earth. It created a bridge between spacecraft observation and laboratory truth. And before that capsule could rest in the Utah desert, before the sample could be opened under careful protection in Houston, the mission had to begin as a launch from the coast of Florida, riding an Atlas V rocket away from Earth toward a small near-Earth asteroid, waiting in darkness. From that bridge between spacecraft observation and laboratory truth, the story moves backward to its first visible flame. Before Bennu was a returned witness, before its grains were sealed inside clean rooms at NASA Johnson Space Center, before the Utah desert became the landing place for material older in context than any human memory, OSIRIS-REx was a spacecraft waiting on the coast of Florida. It stood at Cape Canaveral, not as a mythic machine built to uncover a hidden human past, but as a carefully engineered response to a quieter question. If the early solar system had left clues inside small, carbon-rich bodies, could we go to one, touch it briefly, and bring part of it home? On September 8, 2016, NASA launched OSIRIS-REx from Cape Canaveral, Florida, aboard an Atlas V rocket. The scene had all the surface language of science fiction: a tower of fuel and metal, white vapor moving in the night air, guidance systems locked onto a target that no human eye could see from the launch pad. But the mission was not chasing a tomb. It was not going out to open a stone coffin in space. It was beginning a deliberate expedition to a near-Earth asteroid, a small dark body named Bennu. That distinction matters because false stories often compress space into theater. They make an asteroid feel like a room, a capsule, a hiding place. They make the voyage feel like a secret rescue operation from deep time. The real mission was stranger because it was harder. OSIRIS-REx had to leave Earth, travel across interplanetary space, match paths with a small object moving around the sun, study it closely, choose a place to touch, collect loose surface material, and eventually return that material to Earth without treating it like ordinary dust. Every step depended on navigation, patience, and restraint. The launch from Florida was not the ending of uncertainty. It was the beginning of a long outward arc. NASA later described the spacecraft's journey to Bennu as about 1.2 billion miles, or 2 billion kilometers. That distance is difficult to hold in the mind because it does not behave like distance on Earth. It is not a highway stretched straight from one place to another. It is a path shaped by orbits, timing, gravity, and the moving geometry of planets and asteroids. Bennu was not sitting still, waiting in darkness like a monument. Earth was moving. Bennu was moving. The spacecraft had to move in a way that allowed their paths to meet. This is one of the quiet truths that gets lost when a rumor becomes louder than the mission. Spacecraft do not simply point at an asteroid and fly toward it as if crossing an ocean to a fixed island. They are released into a system already in motion. The sun dominates the choreography. Earth circles it. Bennu follows its own near-Earth path. OSIRIS-REx had to become part of that moving system, leaving Cape Canaveral with enough precision that years later it could approach an object only a fraction of the scale of familiar landscapes. In a cinematic version of the false claim, the asteroid would be enormous, hollow, and dramatic inside, large enough to conceal a human shape and old enough to break biology. But the real target was powerful for the opposite reason. Bennu was small. It was not a world with cities beneath its crust or chambers waiting to be opened. It was a near-Earth asteroid, a dark remnant whose surface could preserve chemical information from the early solar system. The mission's ambition was not to find something human where humans could not belong. It was to reach something non-human and ancient enough to help explain what kinds of materials were available before life on Earth emerged. That is where the scale becomes unsettling in a more truthful way. A human skeleton would make the story smaller. It would drag Bennu into our own timeline and force it into the shape of a familiar mystery. A voyage of 1.2 billion miles to collect asteroid material asks us to do something less comfortable. It asks us to imagine that the meaningful evidence may not resemble us at all. It may be powder. It may be minerals. It may be carbon-bearing chemistry and altered rock. It may be a record that has no face, no bones, no body, and yet carries information from a time when planets were still assembling their histories. OSIRIS-REx traveled outward for more than 2 years before reaching Bennu. In December 2018, the spacecraft arrived at the asteroid after that long journey through interplanetary space. Arrival did not mean landing. It meant coming close enough to begin the careful work of proximity, observing, measuring, mapping, and preparing for the later act of sample collection. The spacecraft had crossed an enormous distance, but the mission's most delicate phase was still ahead. It had to understand the small body it had come to visit. The word arrival can sound simple, almost ceremonial, as if a ship pulls into harbor. But Bennu was not a harbor. It was a moving, irregular asteroid with a surface that would later prove central to the mission's drama. OSIRIS-REx had to operate in the weak gravity environment around a small object, close enough to study it, cautious enough not to lose the precision needed for sampling. The achievement was not only reaching Bennu, it was reaching Bennu in a way that turned a distant target into a navigable, observable place. This is the true architecture of the story. Cape Canaveral was the departure point. The Atlas V was the first force that lifted the spacecraft away from Earth. The journey, measured in billions of kilometers, was the long passage between intention and encounter. December 2018 was the moment the mission changed from pursuit to presence. And Bennu, small and dark, became not a stage for a fabricated corpse, but the object of a patient scientific investigation. The institutions behind this work mattered because the mission was not a single dramatic act. NASA led it through a network of expertise: spacecraft operations, planetary science, instrument teams, curation planning, and later laboratory analysis. The University of Arizona played a major scientific role. NASA Goddard Space Flight Center and NASA Johnson Space Center were part of the larger structure that turned the mission from a launch into a sample return. Even before the capsule came home, the mission had already required years of planning around one central principle: if ancient material could be returned from Bennu, it had to be protected well enough that scientists could trust what it said. That trust began with the outward journey. A careless expedition would not have been enough. A spectacular flyby would not have been enough. The purpose was not simply to see Bennu, but to know it well enough to collect from it. The spacecraft had to carry instruments capable of studying the asteroid before contact. It had to gather information that would help scientists choose where to sample. It had to transform a distant, carbonaceous object into a mapped environment where a future touch-and-go maneuver could be attempted. There is a kind of suspense in that restraint. The mission took years before it ever gathered a single grain. It did not rush to the surface. It did not drill into a hidden chamber. It did not confirm a sensational image. Instead, it approached an ancient object and began the disciplined work of learning its shape, its behavior, and its surface. In a louder story, that patience might feel like delay. In the real story, it was the point. Science was not trying to force Bennu to become a legend. It was trying to let Bennu remain itself long enough to be understood. And this is why the launch and arrival belong at the center of the episode's arc. The truth is not only what OSIRIS-REx eventually brought back. The truth is also what it took to get there: a launch from Cape Canaveral on September 8, 2016, an Atlas V rising from Florida, a years-long route through space, an arrival at Bennu in December 2018 after about 1.2 billion miles or 2 billion kilometers of travel. These are not decorations around the discovery. They are the evidence of intent. The mission was built around a small near-Earth asteroid, not around a hidden human past. Its path was planned through real celestial mechanics, not rumor. Its target was a body whose value came from its chemistry and preservation, not from any imagined anatomy. By the time OSIRIS-REx arrived, Bennu had already become something more interesting than a fictional tomb. It had become a place that could be studied closely, a dark object holding material from the earliest chapters of the solar system. The spacecraft had crossed the distance. The false story would have us look for bones. The real mission asked us to look more carefully at the asteroid itself, its scale, its darkness, its carbon-rich nature, and the ancient record locked inside its surface. Bennu was waiting, not as a grave, but as an archive. Bennu was waiting, not as a grave, but as an archive. That distinction matters because an archive is not passive. It does not have to contain a body to contain a history. It can hold fragments, textures, chemical traces, and silences that become meaningful only when someone learns how to read them. In the case of asteroid 101955 Bennu, the pages were not paper. They were grains of regolith, dark minerals, carbon-rich material, and dust tied to the early solar system. NASA describes Bennu as a near-Earth asteroid, roughly 1,600 feet across, or about 492 meters. On a human scale, that is large enough to become a landscape. On a planetary scale, it is almost nothing. A small, dark body moving through space, not bright enough to dominate the sky, not massive enough to shape worlds, not famous until a spacecraft crossed the distance to meet it. But small does not mean simple. Bennu belongs to the category of objects that planetary scientists treat with unusual care because of what they may preserve. Carbon-rich asteroids are not just rocks in the ordinary sense. They are remnants, carriers, survivors of the earliest period of solar system chemistry. They can hold minerals changed by water, organic molecules, and ancient dust in combinations that help reconstruct conditions from a time before Earth became the restless planet we know. This is where the false skeleton story fails in a deeper way than simple exaggeration. It imagines Bennu as a tomb, as if the scientific value of an asteroid would come from finding something shaped like us hidden inside it. But Bennu's real power comes from being unlike us. It comes from being old in a chemical sense, primitive in a planetary sense, and relatively preserved compared with the surface of Earth. Earth is alive with change. Its crust is broken, recycled, buried, melted, lifted, weathered, and reworked. Water runs through it. Heat rises through it. Plate tectonics carries old rocks downward and brings new rock upward. Atmosphere, oceans, biology, and time collaborate in a constant act of overprinting. Earth is magnificent, but it is not a quiet storage vault. Many records from the earliest solar system have been erased here or altered beyond easy recognition. A carbon-rich asteroid can be different. It can behave like a sealed archive, not perfectly untouched, not magically frozen outside all change, but protected in ways Earth is not. Its material may preserve chemistry from the era when planets were forming, when dust and ice and organic compounds were being sorted, heated, altered, and assembled into larger bodies. To study such material is not to open a coffin. It is to open a record. That is why Bennu became the center of the OSIRIS-REx story. Not because it promised a shocking relic of a human past, but because it offered something scientifically stranger, a way to examine the raw ingredients and altered minerals of an ancient world-building environment. A dark archive does not need a skeleton to be dramatic. Its drama is molecular. Its suspense is mineralogical. Its plot is written in carbon, water-bearing minerals, salts, and dust. From orbit, Bennu did not present itself as a smooth place waiting for an easy landing. It was a small asteroid, with a surface that had to be mapped, judged, and understood. OSIRIS-REx was not chasing myth. It was surveying a real object, with real hazards and real scientific promise. Every close observation added texture to the archive. The asteroid was not simply a point in space anymore. It had shape. It had surface features. It had places that could be named, compared, and considered as possible sampling sites. And still, the most important part remained hidden at the scale of grains. That is one of the quiet reversals in this story. The viral claim reaches for the largest possible image, a human skeleton, something instantly recognizable, something that turns the asteroid into a forbidden chamber. The real science moves in the opposite direction. It becomes more powerful as it becomes smaller. A grain of returned material can matter more than an imagined bone because it can be placed under instruments on Earth, measured, compared, and questioned with precision. Bennu's identity as a near-Earth asteroid also matters. It is close enough, in orbital terms, to become reachable by a spacecraft mission, yet ancient enough in its material context to connect scientists with the early solar system octal. It is both near and remote, nearby in the architecture of mission planning, distant in the history it preserves. That tension gives Bennu its cinematic weight. It is not a faraway planet with oceans and clouds. It is a dark, compact witness passing through the inner solar system with records locked in its loose surface. The archive metaphor also helps keep the timeline honest. Bennu and its parent material are discussed in the context of roughly 4.5 billion years of solar system history. That does not mean a human story can be smuggled into it. Homo sapiens belongs to a vastly younger chapter of time. Human fossils such as those discussed from Jebel Irhoud, Morocco, are on the order of hundreds of thousands of years old, not billions. Bennu's value is not that it contains a human past before humans existed. Its value is that it contains chemical clues from before Earth's surface became the world that could later host humans at all. The word archive also carries caution. An archive does not interpret itself. It preserves traces, but scientists must decide what those traces mean through careful analysis. Minerals can imply histories of heat, water, and alteration. Organic molecules can indicate chemistry associated with life on Earth without proving life existed on the asteroid. Ancient grains can carry origins older than the bodies that now contain them. Each piece of evidence has to be handled with restraint. That restraint is not less exciting. It is more exciting because it means the story survives contact with reality. When NASA and its partners talk about Bennu material, they are not describing a mythic chamber. They are describing carbonaceous asteroid material, regolith, hydrated minerals, organic chemistry, and dust. They are describing something that can help test ideas about how the ingredients associated with biology were distributed before life existed on Earth. This is not a skeleton story. It is a prebiotic chemistry story. It is about conditions, ingredients, and possibilities, not bodies. In science fiction, the archive is often a place where a civilization leaves a warning. Bennu is quieter than that. It carries no carved message. It has no walls, no inscriptions, no deliberate design. Yet it still functions like a message from deep time, because nature has written into it a record of processes that occurred when the solar system was young. Its darkness is not emptiness. Its carbon-rich composition is part of what makes it speak. And OSIRIS-REx was built to listen. By the time the spacecraft studied Bennu closely, the mission had become a negotiation with scale. A spacecraft from Earth had reached a body only about 492 meters across. It had to understand an asteroid small enough to seem fragile against the vastness around it, but important enough to change laboratory science on Earth. The target was not a world to conquer. It was a surface to approach with delicacy. That delicacy would become essential. To read the archive, OSIRIS-REx could not simply admire Bennu from a distance forever. It had to collect material. It had to make contact with a surface that had never been handled by human hands, choose a place where the archive could be sampled, and then retreat with something real. Among the named places on Bennu, one would become central to that moment: Nightingale. There, the quiet archive would stop being only a distant, carbon-rich asteroid and become a physical sample. Not through a landing in the usual sense, not through drilling into a tomb, but through a brief, careful touch using a mechanism designed for an encounter measured in seconds. The archive had been found. The next question was whether it could be opened without breaking the trust of the evidence inside. To open the archive without damaging its meaning, OSIRIS-REx needed a kind of restraint that does not belong to most heroic space stories. It was not going to plant legs on Bennu and stand there like a lander on a solid plane. It was not going to settle into dust, unfold ramps, and begin digging as if the asteroid were a small version of the moon. Bennu had already shown itself to be stranger and rougher than that, a small, dark, carbon-rich body whose surface mattered precisely because it had been left alone. So the mission's crucial act had to be almost paradoxical. The spacecraft had to touch Bennu, but not stay. It had to disturb the surface enough to collect material, but not so much that the evidence lost its value. It had to turn a distant asteroid into a physical sample, while treating that asteroid less like a destination than a witness. That is why the moment at Nightingale carries so much weight. On October 20, 2020, OSIRIS-REx moved toward the primary sampling site on Bennu, a place named Nightingale. The name sounds almost too delicate for the scene, a bird name placed on a rubble-strewn asteroid moving through space, attached to a patch of ancient carbonaceous material far from Earth. But the delicacy fits. Nightingale was not a landing zone in the ordinary sense. It was a target for contact, a place where the spacecraft would perform a touch-and-go sampling maneuver using the touch-and-go sample acquisition mechanism, often abbreviated TAGSAM. The language is technical, but the idea is dramatic. Touch, collect, leave. That sequence separates OSIRIS-REx from the familiar image of exploration. In older stories, arrival often means possession. A ship reaches land. A flag goes down. A base is built. A crew steps out onto new ground. But Bennu did not invite that kind of certainty. It was small, irregular, and ancient, with a surface that had become scientifically precious before anyone knew exactly what was hidden in its grains. The spacecraft was not there to conquer the asteroid. It was there to borrow a fragment of it. In that sense, Nightingale was less like a landing site and more like the keyhole of an archive. For years before that instant, OSIRIS-REx had been a machine of patience. It launched from Cape Canaveral, Florida, on September 8, 2016, and arrived at Bennu in December 2018 after a journey NASA described as about 1.2 billion miles, or 2 billion kilometers. By the time it reached the asteroid, the mission had already crossed a scale that makes most human myths feel small. But distance alone was not the achievement. The deeper challenge was precision. Bennu is only about 1,600 feet, or 492 meters across. That makes it large enough to be a world in the imagination, but small enough to resist many Earth-based assumptions. Its gravity is not the gravity of a planet. Its surface is not a familiar floor. The spacecraft had to operate around a body that was both an object and a place, both a point of light in astronomical terms and a complicated landscape in engineering terms. Nightingale became the focus because the mission required a place where the spacecraft could safely make its brief contact and gather material worth returning. Every part of that sentence matters. Safe contact was not enough if the sample failed to represent the asteroid's scientific promise. Scientific promise was not enough if the spacecraft could not touch and retreat. The mission had to solve both problems at once. And all of it led to a moment measured not by landing legs or footprints, but by the meeting of a mechanism and a surface. TAGSAM was the instrument built for that meeting. The full name, Touch and Go Sample Acquisition Mechanism, explains the philosophy of the act. It was not a drill meant to bore deep into a buried chamber. It was not a claw designed to seize a relic. It was a sampling system made for a brief encounter with regolith, the loose surface material that covers worlds like Bennu. The goal was to collect asteroid material and bring it home, not to interpret it instantly in place. That distinction becomes important because it pushes back against the false skeleton story in a quiet way. A rumor imagines revelation as something visible and theatrical, a body in the rock, a shape that can be recognized at a glance, a secret so large it seems to break history. OSIRIS-REx worked in the opposite direction. Its revelation depended on restraint, contamination control, and laboratories on Earth. The mission did not need to see a human form in the asteroid. It needed grams of material clean enough to ask careful questions. At Nightingale, the spacecraft performed the action that made those questions possible. The drama of the maneuver comes from how little margin there was between success and failure. To touch an asteroid is not like touching a museum case. It is more like touching a page so old and fragile that the act of reading it might alter it. Yet without contact, the page remains closed. OSIRIS-REx had already mapped and studied Bennu from orbit, but remote observation could only go so far. Instruments on a spacecraft can reveal a great deal, but a returned sample can be studied with tools too large and sensitive to fly across space. That was the scientific wager behind the entire mission. So the spacecraft descended toward Nightingale, carrying the hopes of years of planning, engineering, and planetary science. Around Bennu, there was no atmosphere to soften the moment, no blue sky, no ground crew watching from nearby hills. There was only the small, dark asteroid, the spacecraft, the planned route toward contact, and the knowledge that this was the hinge between observation and evidence. Before the touch, Bennu was a studied object. After the touch, if the maneuver worked, Bennu would become something else, a source of material already bound for Earth. That transformation is easy to overlook because it sounds simple. OSIRIS-REx collected material from Bennu on October 20, 2020. A sentence like that is clean, almost administrative. But inside, it is the crossing of a boundary that human beings had imagined for centuries. Material that formed in the early solar system, preserved in a carbon-rich asteroid, was no longer only something to be inferred from telescopes and spacecraft instruments. It had been physically gathered. The asteroid had, in a sense, answered. Not with bones, not with a skeleton, not with a hidden human past pressed into stone. It answered with regolith, with carbonaceous asteroid material, with the promise of minerals and molecules that would later be examined under controlled conditions. The touch at Nightingale did not reveal the inventory immediately. It created the possibility of the inventory. That is why the maneuver deserves to be treated as a cinematic hinge. It is the moment where the story changes state. Before Nightingale, the episode belongs to approach, launch, cruise, arrival, mapping, choosing, waiting. After Nightingale, the story begins to lean homeward, toward the sealed capsule, the Utah desert, NASA Johnson Space Center in Houston, Texas, and the slow work of analysis. The spacecraft did not linger on Bennu like an explorer standing in a ruin. It touched and went. That phrase has a strange emotional force because it contains both intimacy and refusal. OSIRIS-REx came close enough to disturb an ancient surface, yet it did not pretend to own the place. It took what the mission was designed to take, then moved away, preserving the sample's value by beginning its long path toward Earth. For a science fiction version of this story, Nightingale might have been the mouth of a chamber. The contact might have opened a door. A probe might have uncovered a shape that should not exist, a human skull sealed inside a body older than Earth. But the real scene is more austere and more powerful. A spacecraft reached down to a carbon-rich asteroid and gathered grains that could carry records of water-altered minerals, organic chemistry, and early solar system processes. The wonder is not that Bennu contains something human. The wonder is that something so far from human history could still matter so deeply to the question of how worlds become chemically interesting. By the time the sample left Bennu, the false skeleton claim had already become unnecessary. The mission had produced a better mystery, one that did not require breaking biology or time. What exactly had Nightingale given to the spacecraft? What traces were sealed inside that material? What would survive the journey, the capsule return, and the careful opening under laboratory conditions? The touch-and-go moment did not answer those questions. It made them real. It turned a dark surface into a sample, and a sample into evidence waiting for human instruments to read. When that evidence finally came into view, the story would move away from imagined remains and into the actual contents of Bennu: carbon, water-bearing minerals, salts, and organic molecules that were never bones, but were far stranger than an ordinary rock. When the evidence finally came into view, it did not look like the ending promised by the rumor. There was no rib cage folded inside a stone chamber. No skull, no vertebrae, no human outline waiting beneath asteroid dust. The sample from Bennu did not turn into a crime scene or a tomb. It turned into something quieter and scientifically more difficult to dismiss. Inside the returned material, NASA's initial analysis found high carbon content and evidence of water-bearing minerals. That was the first great correction to the myth. The real discovery was not anatomical. It was chemical. The sample was not speaking in the language of bones, but in the language of minerals and molecules, the kind of record that has to be read with laboratory instruments, clean rooms, and patient comparison. This is where the story becomes stranger than the false headline, because carbon and water-bearing minerals are not decorations. In planetary science, they are clues. Carbon is central to organic chemistry. Water-bearing minerals suggest that water once interacted with rock on Bennu's parent body, changing it from within. Together, they point toward processes that were active long before humans existed, long before fossils, long before the familiar surface of Earth became a place where a skeleton could ever be made. The sample returned by OSIRIS-REx was curated at NASA Johnson Space Center in Houston, Texas, where the purpose was not to make a dramatic announcement as quickly as possible. The purpose was to preserve context. The material had crossed space inside a sealed capsule and landed at the Department of Defense Utah Test and Training Range on September 24, 2023. From that moment, its value depended on careful handling. A trace contaminant from Earth could confuse the story. A fingerprint, a fiber, a careless exposure could add modern chemistry to ancient material. So the Bennu sample had to be treated less like treasure and more like testimony. And what that testimony began to reveal was an inventory of early solar system chemistry. Later reporting and laboratory work described hydrated minerals and clay minerals. These are not exotic in the science fiction sense of glowing crystals or engineered artifacts. Their importance is deeper than that. Hydrated minerals contain water in their structure or show that water was involved in their formation. Clay minerals often form when water alters rock. In a sample from a carbonaceous asteroid, that matters because it suggests that the parent material of Bennu was not always dry and inert. At some stage in its history, water was part of the chemistry. The inventory did not stop there. Researchers also described sodium-rich salts, carbonates, sulfates, chlorides, and fluorides. These names can sound technical, almost too ordinary to carry narrative weight. But salts are powerful witnesses. They can point to fluids that once moved through material, dissolved compounds, concentrated them, and then left minerals behind as conditions changed. Sodium-rich salts and related mineral groups are part of the emerging picture that Bennu's parent body may have contained briny environments, places where liquid water and dissolved minerals interacted before the material became the rubble and dust sampled at Nightingale. None of this means there was an ocean inside Bennu as it exists today. None of it means there were creatures swimming in asteroid caverns. The careful language matters. The evidence is not life. It is evidence of chemical environments. It is the difference between finding a kitchen and finding a meal already cooked, between finding letters of an alphabet and finding a written confession. Bennu's material contains signs of conditions and ingredients, not a body. Then come the organic molecules. NASA's later reporting described amino acids in Bennu samples, including 14 of the 20 used by life on Earth to make proteins. That sentence is easy to inflate and dangerous to oversimplify. Amino acids are associated with biology on Earth, but they are not themselves bones, muscles, cells, or organisms. They are molecules. They can be part of life's chemistry without being proof that life was present. Their presence in Bennu material is exciting because it shows that important organic compounds can exist in ancient asteroid material, not because it turns the asteroid into a fossil. The same caution applies to the other categories reported from Bennu: amines, formaldehyde, carboxylic acids, polycyclic aromatic hydrocarbons, N-heterocycles, nucleobases, and sugars. Each term adds another layer to the chemical portrait. Amines and carboxylic acids are organic compounds relevant to broader prebiotic chemistry. Formaldehyde is a simple organic molecule that can participate in chemical pathways leading toward more complex substances. Polycyclic aromatic hydrocarbons are carbon-rich structures found in space environments and in meteorite chemistry. N-heterocycles include ring-shaped molecules containing nitrogen, a feature that appears in many biologically important molecules on Earth. The nucleobases are especially striking because NASA reported all 5 used by terrestrial life to store and transmit genetic information in DNA and RNA: adenine, guanine, cytosine, thymine, and uracil. In the mythology of the skeleton claim, that kind of detail would be twisted into a message, as if the asteroid carried a genetic signature from a lost person or an alien archive. But the scientific meaning is more careful and, in a way, more profound. Nucleobases are not DNA by themselves. They are not instructions without a larger system. They are components that, on Earth, life uses in genetic molecules. Finding them in Bennu material helps scientists explore how such components could have been available in the early solar system. Sugars were also described in later NASA reporting, including ribose and other sugars. Again, the boundary has to stay clear. Ribose is important in biology because it is part of RNA, but the presence of ribose in asteroid material is not evidence that Bennu held living cells. It is evidence that chemistry related to life's molecular toolkit can arise or survive in extraterrestrial material. That is not a small claim. It simply is not the claim the rumor made. This is why the phrase building blocks of life needs care. It can be useful, but only if it is not allowed to become a shortcut for saying life was found. A brick is not a house. A letter is not a poem. An amino acid is not a skeleton. A nucleobase is not a genome. A sugar is not a cell. Bennu's sample contains ingredients and chemical records, not remains. And this distinction makes the real discovery more valuable, not less. A skeleton would be sensational, but it would also break almost everything we know about time, biology, and human evolution. It would demand evidence far beyond a rumor, and no such evidence exists from NASA or the scientific sources tied to OSIRIS-REx. The actual Bennu sample does not require that kind of impossible leap. It fits into a larger, testable story. Carbon-rich asteroids can preserve ancient materials, water can alter rock, brines can concentrate compounds, organic molecules can form, move, or survive in small bodies of the solar system, and some ingredients associated with life on Earth were present in places that were not Earth. That is the real strangeness. The sample is not a relic of a human past. It is a record from a time before the human past could begin. Its importance comes from the way it narrows the distance between planetary formation and prebiotic chemistry. It allows scientists to ask what kinds of molecules were available when the solar system was young, how water changed primitive material, and how asteroids may have delivered or preserved compounds that later became relevant on worlds like Earth. In that sense, Bennu is not empty because it contains no bones. It is full because it contains context. The inventory reads like the table of contents of an ancient chemical archive. Hydrated minerals, clay minerals, sodium-rich salts, carbonates, sulfates, chlorides, fluorides, amino acids, amines, formaldehyde, carboxylic acids, polycyclic aromatic hydrocarbons, N-heterocycles, nucleobases, and sugars. Not a body, not a fossil, not proof of alien biology, but a set of clues pointing toward the environments and reactions that shaped matter before life took hold on Earth. The false story imagined a human figure hidden inside an asteroid. The real sample offers something less theatrical and more enduring, traces of carbon, water, salts, and organic chemistry locked in material from the early solar system. To understand why that matters, the next step is to follow the water, not as an ocean with waves and shores, but as a vanished force written into minerals that still remember it. To follow the water in Bennu, we have to imagine it almost by its absence. Not blue water, not rivers crossing an asteroid plain, not an ocean beneath the sky. Bennu, as OSIRIS-REx found it, was a small, dark, rubble-rich world moving through near-Earth space, not a place with waves, rain, or a visible shoreline. And yet, when NASA began describing the returned material from the capsule that landed in Utah on September 24, 2023, one of the first striking details was not only carbon. It was evidence of water-bearing minerals. That phrase sounds modest, almost hidden behind technical language. But in planetary science, water-bearing minerals are not a small detail. They are a record. They tell scientists that somewhere in the earlier history of the material, water was present long enough to alter rock. It interacted with minerals. It changed them. It left a signature that could survive long after the liquid itself was gone. This is where Bennu becomes stranger than a simple stone. The sample curated at NASA Johnson Space Center in Houston, Texas, did not need to contain a drop of liquid water to preserve a watery past. Minerals can carry that past structurally and chemically. Hydrated minerals and clay minerals are not little bottles of ocean sealed inside dust. They are materials whose formation or alteration is tied to water. Their presence points back to an environment where rock and liquid were once in contact. That distinction matters because the real story is not that Bennu was a tiny ocean world, as we would picture one in science fiction. It is that Bennu's parent body, the larger object from which Bennu's material ultimately came, appears to have experienced water-driven alteration. The asteroid we see now is a survivor, a fragmentary archive. Its grains can preserve conditions older than the modern rock pile itself. They can carry mineral evidence from a parent body that was not dry and inert, but chemically active in the presence of water. In the false skeleton story, the asteroid becomes a tomb. In the real science, it becomes something more subtle, a remnant of an ancient wet chemistry experiment. NASA's initial analysis gave the public the broad outline. The Bennu material was rich in carbon, and it showed evidence of water-bearing minerals. Later work gave that outline a more detailed texture. Smithsonian-led research described signs that evaporated water had left behind briny salt minerals in the Bennu material. That idea changes the scene again. It asks us to imagine water not as a permanent sea, but as a temporary chemical agent. Water moves through material, dissolves ingredients, carries ions, alters minerals, and then disappears. When it evaporates or is otherwise lost, salts can remain. A vanished liquid leaves a mineral echo. Those salt minerals are important because water by itself is only part of the story. Liquid water can enable reactions, but water mixed with salts can create brines, and brines are chemically powerful environments. They can concentrate substances that might otherwise remain too diluted to interact often. They can change how molecules move, how minerals dissolve, and how certain compounds become available for further reactions. In a small ancient body, this kind of environment would not need to resemble a lake on Earth to matter. It could be localized. It could be temporary. It could exist in pores, cracks, or small wet regions within rock. And still, it could shape chemistry. This is why the water-altered minerals in Bennu are so much more than background information. They help scientists ask what kind of chemical setting existed before the material became part of the asteroid sampled by OSIRIS-REx. Was it merely cold dust that stuck together and remained unchanged? Or was it dust and rock that, for some period, met liquid water and salts and began to rearrange? The evidence points toward rearrangement. The language has to stay careful here. Water-bearing minerals do not mean life. Briny salts do not mean organisms. Clay minerals are not fossils. A wet environment is not the same thing as a living environment. The returned Bennu sample does not overturn the human timeline, and it does not place biology inside an asteroid. What it does is show that some of the same broad conditions that interest origin of life researchers were present in primitive solar system material: carbon-rich chemistry, water alteration, salts, and organic molecules. That is not a skeleton. It is not even a cell. It is a setting. And settings matter. On Earth, the story of life is inseparable from water, but Earth is a restless planet. Plate tectonics, weathering, heat, pressure, oceans, and biology itself have spent billions of years rewriting the surface record. Very old chemical clues can be destroyed, buried, transformed, or contaminated by later processes. Bennu offers a different kind of record, not untouched in every possible sense, but preserved in a way that lets scientists study ancient solar system chemistry outside the overwhelming activity of Earth. A returned sample makes that possible with unusual precision. Instruments too large and sensitive to fly on a spacecraft can examine grains from Bennu in laboratories. Teams can compare mineral structures, chemical compounds, and tiny associations between materials. They can look not just at what is present, but at what sits beside what. In a sample like Bennu's, context can be as meaningful as inventory. A molecule next to a salt grain, a hydrated mineral beside a carbonate, a clay mineral associated with organic material. These relationships help scientists reconstruct history. The asteroid material becomes less like a pile of ingredients and more like a map of processes. Water changes rock by making it participate. Dry minerals can remain isolated from one another for long stretches of time. Add liquid water and the barriers soften. Ions move. Compounds dissolve. New minerals form. Old minerals alter. Organic molecules can be transported or concentrated. Salts can appear as the water disappears. The result is not life, but it is chemistry with motion, chemistry with pathways, chemistry with memory. That is why Bennu's water story feels cinematic without needing to become fantasy. Somewhere in the deep past of the solar system, before Earth's surface became the world we know, before humans, before bones, before fossils, there were small bodies containing ice, rock, carbon, and heat enough for change. In some of those bodies, ice may have melted. Water may have moved through dark material. Salts may have accumulated as fluids evaporated. Minerals may have formed that could later survive the breakup, reassembly, and long journey that brought Bennu into near-Earth space. By the time OSIRIS-REx reached Bennu in December 2018, none of that ancient wet activity was visible as water. The spacecraft saw a dark asteroid. The sample mechanism touched regolith at Nightingale on October 20, 2020. The capsule came home carrying grams of material, not an ocean. But inside those grains were mineral signs that water had once mattered. This is the quiet reversal at the heart of the chapter. The rumor searched for a body because a body is easy to picture. Science found a vanished environment because environments are harder to see. They have to be inferred from what remains after the obvious thing is gone. Water without an ocean is exactly that kind of clue. It asks us to think beyond surfaces. A dry asteroid today can preserve evidence of wet alteration yesterday, if yesterday means the ancient past of planetary formation. A handful of black grains can contain minerals that remember fluid. Salts can mark the final stage of evaporation. Clay can mark interaction. Carbon-rich compounds can sit inside a record shaped by water rather than sealed away from it. And once salts enter the story, the chemistry becomes even more specific. Sodium-rich salts, carbonates, sulfates, chlorides, and fluorides are not dramatic in the way a false skeleton is dramatic. They do not look like a message. They do not point to a hidden civilization, but they may point to brines, to concentrated chemical spaces where life-related ingredients could meet and change before life itself existed on Earth. The water is gone. The minerals remain. And in those remaining salts, the next clue begins to sharpen. The water is gone, but the salts remain, and salts are rarely just decoration in a rock. They are residues. They are endings. They are what can be left behind when a liquid once carried dissolved material through small spaces, then disappeared. In the Bennu sample, that idea matters because the story is no longer only about whether water touched ancient minerals. It becomes more precise than that. It becomes a question of what kind of water, what it carried, what it left behind, and what chemical opportunities may have existed inside Bennu's parent body long before Earth had a human witness. This is where brine enters the investigation. Not as a creature, not as an alien sea, not as a hidden biological chamber inside an asteroid. Brine is simply salty water, water loaded with dissolved ions, the kind of fluid that can move through minerals, concentrate chemicals, and then vanish into a mineral record. On Earth, brines can appear in salt flats, evaporating basins, underground pockets, and other settings where water and dissolved salts are forced into close contact. Bennu is not being described as a miniature Earth, and scientists are not claiming that it had lakes, beaches, or living ecosystems. The point is quieter and more important. When researchers see certain salt minerals in returned asteroid material, they can ask whether those minerals preserve the signature of evaporated brines. Smithsonian-led work on Bennu material described evidence that evaporated water left briny salt minerals in the sample. That phrasing is careful. It does not say that Bennu carried life. It does not say that organisms swam in asteroid water. It says the mineral evidence points toward a chemical environment where water and salts once interacted, then dried away, leaving traces behind. The specific minerals matter. Sodium-rich salts, carbonates, sulfates, chlorides, and fluorides each add a little more shape to the story. They are not dramatic by themselves. A carbonate does not look like a bone. A sulfate does not look like a fossil. A chloride or fluoride does not speak in symbols. But together, in carbonaceous asteroid material returned by OSIRIS-REx, they become evidence of a process. They suggest that dissolved chemicals were once mobile enough to separate, combine, and crystallize as fluids changed. That is the brine clue. Sodium-rich salts are especially suggestive because sodium is a familiar participant in salty solutions. In a dry sample, sodium-bearing salts can be like the outline of a vanished fluid. They do not preserve the water itself, but they can preserve a memory of what the water carried. Carbonates point to reactions involving carbon-bearing chemistry and minerals. Sulfates add another class of dissolved material, another chemical path. Chlorides and fluorides widen the picture still further. None of these minerals alone proves a single simple environment. Bennu's parent body was not observed directly in its ancient wet phase, and its history has to be reconstructed from mineralogy, chemistry, isotopes, and models. But the mixture of these salts gives scientists a way to infer that water did more than briefly touch rock. It may have created concentrated chemical spaces. Those spaces are the reason the discovery feels stranger than the false skeleton claim. A skeleton would be a simple story if it were real. A body, a species, a date, a mystery to solve. But it collapses almost immediately against what we know about human evolution and solar system time. Brines are harder to picture, but they are more scientifically powerful. They are not remains. They are not anatomy. They are not an image that can go viral in a single frame. They are conditions. They are mechanisms. They are environments where ingredients can be brought together, held in contact, altered by minerals, and concentrated as water disappears. In prebiotic chemistry, concentration is a serious problem. Molecules may exist, but if they are too diluted, if they never meet, if they drift separately through too much space, then interaction becomes less likely. Brines change that. As water evaporates, dissolved materials can become more concentrated. Minerals can precipitate. Chemical gradients can form. Surfaces can provide places where molecules attach, react, or rearrange. This does not create life by itself. It does not cross the line from chemistry into biology. But it offers a setting where life-related chemical ingredients could interact before life existed on Earth. That distinction has to stay clear. A chemical setting favorable to interaction is not a fossil. It is not a living cell. It is not proof of alien biology. It is not evidence that something once breathed, moved, reproduced, or left behind a body inside Bennu. When scientists talk about environments where life-related ingredients could interact, they are talking about possibility in a chemical sense, not about discovery in a biological sense. Bennu gives researchers material that may preserve ancient chemical contexts. It does not give them a creature. This is why the returned sample is so valuable. OSIRIS-REx did not just photograph a dark surface and leave scientists guessing from a distance. It delivered material from asteroid Bennu to Earth, where laboratories could examine minerals and molecules with instruments too large and sensitive to fly on the spacecraft. The sample was curated at NASA Johnson Space Center in Houston, Texas, under conditions designed to protect its scientific value. That care matters when the evidence is subtle. A salt grain, an organic molecule, a hydrated mineral, or a trace compound can change the interpretation of a whole environment. And Bennu is not an isolated clue in a vacuum. It belongs to a broader class of carbon-rich asteroids that act like archives of early solar system chemistry. Earth has its own ancient story, but Earth is active. Heat, water, plate tectonics, weathering, biology, and time can erase or overprint older records. A carbonaceous asteroid can preserve a different kind of memory, not untouched in every way, but less rewritten by the long machinery of an active planet. That is why a handful of dark grains can matter so much. They can hold signs of mineral alteration, organic chemistry, and evaporated brines from a time when planets were still assembling their histories. The sci-fi version imagines a hidden chamber. The scientific version imagines pores, fractures, grains, surfaces, and fluids moving through primitive rock. It is smaller, but in some ways more unsettling. No corridor, no skeleton, no ancient astronaut. Instead, a chemical landscape inside a parent body, water dissolving materials, salts forming as fluids changed, carbon compounds present in the same ancient record, minerals documenting conditions that no eye ever saw. This is not a monster story. Brine is not alive. It does not intend anything. It does not search for biology. But brine can act as a stage. It can gather materials that otherwise remain scattered. It can create boundaries between wet and dry, dissolved and crystallized, mobile and fixed. It can leave behind salts that survive long after the liquid is gone. In Bennu's case, sodium-rich salts, carbonates, sulfates, chlorides, and fluorides turn the idea of ancient water into something more textured than a simple yes or no. They let scientists ask what the water was doing. That question is central to the whole real mystery. If Bennu's parent body contained briny fluids, then the asteroid material is not just a frozen box of ingredients. It is a record of interaction. Carbon-rich compounds were not necessarily sitting in complete isolation. Hydrated minerals, clay minerals, and salts suggest a world where rock and water altered one another. Organic molecules, when found in the same broad context, become part of a larger chemical scene. Not life. Not proof of life, but chemistry with movement, concentration, and contact. The false headline asks us to imagine a human past older than Earth. The evidence asks something more grounded and more profound. How far back do the chemical pathways associated with life's ingredients go? Before humans, before animals, before cells, before Earth became the world we know, could small bodies in the early solar system have hosted wet, salty environments where relevant molecules met each other? Bennu does not answer that question with a fossil. It answers with minerals, and minerals speak slowly. They speak through composition, texture, association, and context. A sodium-rich salt beside other alteration products is not a dramatic revelation by itself. A carbonate or sulfate is not a final verdict. Chlorides and fluorides do not turn an asteroid into a biosphere, but together, examined in clean laboratories after a carefully protected sample return, they form a pattern that can be tested. They offer a way to reconstruct vanished fluids and the chemical settings those fluids may have created. That is the discipline the skeleton rumor lacks. The rumor leaps from mystery to body, from ancient rock to impossible human remains. The science moves in smaller steps. It says water-bearing minerals show alteration. It says briny salts may mark evaporation. It says carbon-rich chemistry was present. It says certain environments can help molecules interact. And then it stops before claiming life. That restraint is not weakness. It is the reason the discovery can be trusted. The Brine Clue does not close the case. It opens a more careful one. If salty water once concentrated chemical ingredients in Bennu's parent body, then the sample becomes a record of prebiotic possibility, not biological proof. It becomes evidence that some of the settings relevant to life's chemistry may have existed beyond early Earth, in small, ancient bodies moving through the young solar system. From there, the investigation naturally tightens around the molecules most familiar to biology on our planet. Because once salts and water have given us a possible setting for interaction, the next question is, what ingredients were actually there? Among the most powerful of those ingredients are amino acids, including some used by life on Earth to build proteins. But amino acids are not bones. And that distinction will matter even more. If the Brine Clue gave Bennu a possible setting, then amino acids give that setting a sharper emotional charge. The phrase itself feels close to life. It belongs in biology classrooms, in discussions of cells and proteins, in the quiet machinery of bodies. So when NASA reported that Bennu's samples contained amino acids, including 14 of the 20 used by life on Earth to make proteins, the discovery sounded almost like a threshold. But it was not a skeleton. It was not a hand. It was not a rib cage sealed in stone. It was not the outline of a person carried through space from some impossible human past. It was chemistry. And the difference between those two things is not a small technical correction. It is the line between a false headline and a real scientific revelation. Amino acids matter because life on Earth uses them with astonishing precision. In terrestrial biology, they are among the molecular units that cells link together to build proteins. Proteins then become part of the working structure of life. Enzymes, tissues, signaling systems, and countless microscopic tasks that make organisms possible. That association is why amino acids are often called building blocks of life. But a building block is not a building. A letter is not a book. A brick lying in ancient dust is not a city. That is the first careful step in understanding Bennu. NASA's report did not say that OSIRIS-REx had returned living material. It did not say that the asteroid contained a fossil. It did not say that a body had formed there, died there, and waited inside the regolith until the sample capsule landed in Utah on September 24, 2023. The reported discovery was molecular. Amino acids were present in the returned material from asteroid 101955 Bennu. That is already extraordinary. To see why, we have to hold two ideas at once. On Earth, amino acids are deeply tied to biology. In space and in ancient solar system material, amino acids can also be products or survivors of non-biological chemistry. They can exist before life. They can be part of the inventory from which life-related chemistry draws, without themselves proving that life has appeared. This is where the false skeleton story becomes useful, not because it is plausible, but because it shows how easily the mind jumps from ingredient to organism. A skeleton is a finished biological structure. It implies a body. It implies development, tissue, metabolism, ancestry, death, preservation, and time. A human skeleton, specifically, implies Homo sapiens, a species whose known fossil record reaches back on the order of hundreds of thousands of years, not billions. Amino acids imply none of that by themselves. They imply possibility. They imply that some of the molecular materials familiar from life on Earth were present in an ancient carbonaceous asteroid sample. They imply that the chemistry of the early solar system was not sterile in the simple sense. It held carbon-rich compounds, water-altered minerals, salts, and organics. Bennu's material, curated at NASA Johnson Space Center in Houston, Texas, became a way to examine those ingredients in laboratories on Earth with instruments far more sensitive than anything that could have been carried across space on OSIRIS-REx. The mission's strength was not that it found a dramatic object. Its strength was that it returned a protected sample. The capsule did not need to contain something shaped like life in order to transform the question. A little over 121.6 grams of asteroid material was enough to let scientists ask what chemistry had been preserved, what had been altered by water, what salts remained after brines vanished, and what organic molecules survived in that ancient record. In that context, the amino acids are not a sideshow. They are central. NASA's 2025 reporting described amino acids in the Bennu samples, including 14 of the 20 used by life on Earth to make proteins. That number is striking because it creates a bridge between planetary science and biology. It does not say that Bennu had biology. It says that molecules familiar to biology were part of Bennu's chemical inventory. The distinction is quiet, but it changes everything. If we imagine a skeleton, we imagine a mystery of identity. Who was this? How did they get there? What civilization, accident, or impossible rupture in time placed a human body inside a dark asteroid older in context than human existence by an almost incomprehensible margin? But if we look at amino acids, the question becomes deeper and less theatrical. How widely were life-related ingredients distributed before life emerged on Earth? Did asteroids carry some of those ingredients through the young solar system? Could water and salts inside a parent body have helped concentrate or modify them? Were the raw materials for later biology part of a broader chemical landscape rather than something confined to our planet alone? These questions do not require aliens. They do not require a body. They do not require a hidden chamber inside Bennu. They require patience, clean handling, careful chemistry, and a willingness to be impressed by molecules instead of myths. That can be harder than it sounds. Amino acids are invisible to the eye. They do not give the camera a face. They do not make the sample tray look like a tomb. In a clean laboratory, asteroid material can appear as dark grains, fragments, dust, and small stones. The drama is not in the shape. It is in the analysis. The drama is in realizing that an asteroid, small enough to be measured in hundreds of meters across, can preserve chemical information from the earliest chapters of the solar system. The false headline says, NASA found a human skeleton inside an asteroid. The real evidence says, NASA returned carbon-rich material from Bennu, and analysis found amino acids, among other organic molecules, in a sample associated with water-bearing minerals and ancient salts. The false headline collapses because it tries to turn prebiotic chemistry into anatomy. The real discovery holds because it does not need exaggeration. Amino acids are exciting precisely because they sit near the boundary between geology and biology without crossing it by themselves. They are life-related, not life. They are ingredients, not organisms. They are evidence of chemistry, not evidence of a person. And this matters for how we talk about the origin of life. The origin of life is not simply the moment when a creature appears. It is a long scientific question about transitions, from simple molecules to complex chemistry, from chemistry to self-organizing systems, from non-living matter to biology. Bennu does not answer all of that. It does not hand over the missing scene. But it does provide a physical sample from a carbonaceous asteroid where some relevant ingredients can be studied in their mineral context. That context is crucial. Amino acids alone in a report are interesting. Amino acids alongside hydrated minerals, clay minerals, sodium-rich salts, carbonates, sulfates, chlorides, fluorides, and other organics become part of a more textured story. They suggest that Bennu's parent body was not just a dry rock carrying random dust. It experienced chemical conditions involving water alteration. It preserved residues that can be compared with models of early solar system environments. Still, none of this lets us say that life existed there. Science often becomes most powerful when it refuses to outrun its evidence. That refusal can feel less cinematic than a skeleton, but it is what keeps the wonder intact. If every organic molecule becomes proof of an organism, then the real sequence of discovery is lost. We stop seeing how strange it is that non-living processes can produce molecules associated with living systems. We skip over the very mystery scientists are trying to understand. Amino acids are not bones. They are not even proteins by themselves. They are smaller pieces that biology can use, but biology is a system, not a shopping list. Life requires organization, energy flow, information, boundaries, replication, and chemistry working together in sustained patterns. Finding amino acids is like finding musical notes scattered in ancient dust. It tells us that some of the tones were present. It does not tell us that a song was being played. That is why Bennu is so compelling. It offers notes, not a skeleton, not a corpse from before Earth, not proof of a vanished human story. Instead, OSIRIS-REx brought back a record of molecular possibilities from a small, near-Earth asteroid whose material reaches into the early solar system. The amino acids in that record do not diminish the mystery by being non-biological. They enlarge it. They show that the chemistry associated with life on Earth may have roots in environments far beyond Earth. And once that idea is clear, another discovery becomes even more delicate. Amino acids are not the only familiar molecules reported from Bennu. NASA also described all 5 nucleobases used by terrestrial life to store and transmit genetic information in DNA and RNA: adenine, guanine, cytosine, thymine, and uracil. Those names sound even closer to a message. But molecules can resemble letters without forming words. And in Bennu's dark archive, the presence of those 5 letters will have to be read with the same discipline, not as a signal from a mind, not as DNA from a vanished organism, but as chemistry waiting to be understood. Those 5 names sit at the edge of the story like a code that has not become a sentence. Adenine, guanine, cytosine, thymine, uracil. On Earth, these molecules belong to some of the most intimate systems life possesses. They are part of the language by which organisms store, copy, and transmit genetic information. In DNA, adenine, guanine, cytosine, and thymine help form the molecular archive that guides living cells. In RNA, uracil appears where thymine would be expected in DNA, taking its place in another version of biological information. These are not obscure chemicals to biologists. They are familiar letters in the alphabet of life. That is why NASA's reporting on Bennu feels so charged. The material returned by OSIRIS-REx did not only contain carbon-rich chemistry, water-altered minerals, salts, and amino acids. It also included all 5 nucleobases used by terrestrial life to store and transmit genetic information in DNA and RNA. For a moment, the imagination wants to sprint ahead of the evidence. It wants to see a hidden script. It wants the asteroid to become a bottle from deep time, carrying a message across the solar system. It wants the viral myth to find a new disguise, not a skeleton now, perhaps, but a genetic trace, an alien signature, a fragment of ancient biology buried in black dust. But that is not what the evidence says. The presence of nucleobases in Bennu material is not evidence of DNA strands. It is not evidence of RNA molecules arranged into biological instructions. It is not evidence of cells, organisms, fossils, or intelligence. It does not mean there was a living thing on Bennu. It does not mean a vanished creature wrote itself into the asteroid. It means the molecules associated with genetic systems on Earth can exist in ancient carbonaceous asteroid material. That distinction is quiet, but it changes everything. A letter is not a message. A single character is not a book. Even a complete set of letters is not the same as a written page. The alphabet can sit loose in a drawer without spelling a name. It can be scattered across a table without becoming a confession. In the same way, adenine, guanine, cytosine, thymine, and uracil can be present as chemistry without forming the organized systems that life uses to preserve and transmit information. This is where the Bennu discovery becomes stranger than the false headline, but also more disciplined. A skeleton would be obvious if it were real. Bone has shape. A skull has symmetry. A vertebra carries the architecture of an animal body. But Bennu's actual clues are smaller and more ambiguous. They are molecular. They do not announce themselves as remains. They ask to be interpreted through laboratory work, contamination control, comparative chemistry, and patient caution. That is why the sample return matters so much. OSIRIS-REx did not merely observe Bennu from a distance and guess at its chemistry through reflected light. It brought material back to Earth. The capsule landed on September 24, 2023, at the Department of Defense Utah Test and Training Range near Salt Lake City, Utah. The material was then handled for study at NASA Johnson Space Center in Houston, Texas, where the value of the sample lay partly in its protection, a clean record from asteroid 101955, Bennu, preserved well enough for instruments on Earth to examine details that no spacecraft could fully resolve alone. In that returned material, the 5 nucleobases matter because they sit in the same larger pattern already forming across the mission's findings. Bennu material showed high carbon content, It showed evidence of water-bearing minerals. It held hydrated minerals and clay minerals. Smithsonian-led work described signs of briny salt minerals left by evaporated water. NASA reporting described amino acids, including 14 of the 20 used by life on Earth to make proteins. Now the record expands to include the molecular bases that life on Earth uses in genetic information. The temptation is to connect those points into a living outline. But science does not allow the outline to be filled in just because the shapes feel familiar. Amino acids are not proteins inside a living cell. Nucleobases are not genomes. Salts are not oceans. Hydrated minerals are not habitats by themselves. Each clue matters, but each clue has limits. The excitement comes from their combination, not because the combination proves life, but because it helps scientists explore how life-related chemistry could have been distributed and processed before life existed on Earth. Bennu's parent material belongs to the early solar system story. NASA describes the Bennu sample as roughly 4.5 billion years old in context, preserving ancient material from the time when planets were forming and small bodies were being altered by heat, water, salts, impacts, and motion. In that setting, the presence of nucleobases raises a profound possibility without crossing into fantasy. Some ingredients later used by life on Earth may not have been exclusive to Earth partitionists. They may have been part of a broader chemical inventory available in ancient planetary materials. That does not make life inevitable. It does not mean every asteroid with organic molecules is a seed of biology. It does not mean Bennu was alive, or that Bennu carried a body, or that Bennu held a coded warning from another civilization. What it suggests is more subtle. The raw materials associated with life can arise, persist, or be preserved in environments that are not living. Chemistry can precede biology. The alphabet can exist before anyone writes a story. This is the cinematic contradiction at the center of the chapter. The molecules are deeply familiar because our own bodies depend on genetic systems that use them. Every living person carries DNA, and that DNA uses nucleobases as part of its structure. Every cell depends on the transfer and expression of information. So when the same class of molecules appears in asteroid material, the discovery feels almost personal. It feels as if the asteroid has spoken in a language our bodies already understand. But the asteroid has not spoken. There is no message in the sense that a mind writes a message. There is no sentence. There is no grammar. There is no biological machinery placing nucleobases in order to encode inherited traits. The discovery is not a text. It is a collection of chemical evidence from a small, dark, carbon-rich body that traveled through solar system history long before humans appeared on Earth. That difference is not a technicality. It is the boundary between science and myth. The false skeleton claim collapses because it imagines a human past where there cannot be one. Homo sapiens remains discussed from Jebel Irhoud, Morocco, are about 300,000 years old. Bennu's material reaches back into a context of billions of years. A human body does not fit that timeline. A human skeleton inside Bennu would not be a surprising discovery requiring interpretation. It would be a contradiction demanding impossible assumptions. The nucleobases, however, fit the timeline. They do not require humans. They do not require cells. They do not require aliens. They belong to chemistry, and chemistry was present long before biology as we know it. That is what makes them powerful. They connect the asteroid not to a buried person, but to the prebiotic world of ingredients, reactions, and environments that scientists study when asking how life's raw materials became available. This is where Bennu becomes less like a tomb and more like a laboratory, frozen in fragments. In its grains are records of water-altered minerals and salts that may point back to ancient brines. In its organic molecules are amino acids and nucleobases that overlap with the chemistry used by life on Earth. The pieces do not assemble into an organism. They assemble into a question about distribution. Were such ingredients widespread in the early solar system? Could small bodies have delivered or preserved them? Did environments beyond early Earth help shape the inventory from which life later emerged? Those questions are more useful than the skeleton myth because they can be tested. Returned samples can be measured. Molecules can be identified. Mineral contexts can be compared. Bennu material can be studied alongside meteorites and other asteroid samples, including work connected to JAXA's Hayabusa 2 asteroid sample community. Institutions such as NASA Goddard Space Flight Center, NASA Johnson Space Center, the University of Arizona, the Smithsonian National Museum of Natural History, the Natural History Museum London, the Canadian Space Agency, and others contribute different parts of the investigation. The story is not one shocking reveal hidden in a rock. It is a network of careful measurements expanding what scientists can ask. And the 5 nucleobases sit at the center of that network as symbols of both wonder and restraint. They are familiar enough to feel like a threshold, but they are not enough to cross it. They show that Bennu carried letters associated with life's information systems on Earth. They do not show that Bennu carried the information itself. They are ingredients without instructions, alphabet without syntax, possibility without proof of biology. That may sound less dramatic than a secret skeleton. It is not. It is more unsettling in a quieter way. It suggests that the boundary between lifeless chemistry and living systems may have been approached through materials scattered across worlds, through brines inside ancient parent bodies, through carbon compounds moving in darkness before Earth became a stable stage for biology. It makes life feel less like an isolated miracle and more like a question rooted in cosmic chemistry. Still, the discipline remains the same. Do not turn molecules into bones. Do not turn letters into a message. Do not turn familiarity into evidence of life. Bennu has given scientists adenine, guanine, cytosine, thymine, and uracil in ancient asteroid material. That is enough to deepen the mystery without inventing a civilization behind it. The truth is not that someone wrote inside the asteroid. The truth is that some of the letters life later learned to use were already present in the dark. And once those letters are on the table, another family of molecules begins to matter. Because genetic systems on Earth do not depend on nucleobases alone. The story also turns toward sugars, including ribose, another familiar ingredient reported from Bennu's stone-like archive, and another reminder that the chemistry of life is not the same thing as life itself. After the 5 letters, the chemistry becomes quieter, but not less important. Adenine, guanine, cytosine, thymine, and uracil sound like a code because on Earth, life uses them inside genetic systems. But even those molecules do not work alone. They are not floating symbols in a vacuum. In biology, they are built into larger structures, joined to other chemical parts, arranged by cells, copied by enzymes, and protected inside living systems. One of those other chemical parts is a sugar. That is why later, NASA reporting on Bennu drew attention not only to amino acids and nucleobases, but also to sugars, including ribose. In the language of Earth life, ribose has a special resonance. It is part of RNA, one of the central molecules involved in storing, transmitting, and using genetic information. It is familiar enough to feel almost biological the moment its name appears. But this is exactly where the story has to slow down. NASA did not report life in Bennu. NASA did not report cells. NASA did not report DNA strands, RNA organisms, alien fossils, or a hidden body sealed inside an asteroid. The reporting described molecules, organic chemistry, ingredients associated with life as we know it, found inside ancient carbonaceous asteroid material returned by OSIRIS-REx and studied under careful laboratory conditions. That distinction is not a technicality. It is the whole point. Ribose matters because it belongs to the wider inventory of life's chemistry. But finding ribose is not the same as finding biology. A sugar molecule is not a skeleton. It is not a memory. It is not proof that anything ever breathed, reproduced, sensed, or died on Bennu. It is a chemical clue, and its value depends on keeping it inside the right frame. The false story asks us to imagine a human body inside an asteroid older than Earth. It creates awe by breaking time so violently that the claim cannot survive contact with evidence. The real story works differently. It creates awe by showing that some of the chemistry later used by life on Earth may have existed in small ancient bodies long before life itself appeared here. That is stranger in a more disciplined way. Because Bennu is not a tomb. Bennu is an archive. Its material, delivered to Earth by the OSIRIS-REx sample capsule after landing at the Department of Defense Utah Test and Training Range on September 24, 2023, is being treated as a preserved record of early solar system chemistry. At NASA Johnson Space Center in Houston, Texas, that record can be examined with instruments far more sensitive than anything that could have flown to the asteroid and operated there in isolation. The sample is small in the ordinary sense, 121.6 grams of material. But chemically, it is vast. It contains carbon-rich material. It contains evidence of water-bearing minerals. Later analysis and reporting have described hydrated minerals, clay minerals, sodium-rich salts, carbonates, sulfates, chlorides, fluorides, amino acids, amines, formaldehyde, carboxylic acids, polycyclic aromatic hydrocarbons, N-heterocycles, nucleobases, and sugars. That list can sound like a laboratory inventory, and in one sense it is. But it is also a map of possibility. Sugars belong on that map because life on Earth uses sugars in crucial ways. They can be structural. They can be energetic. They can be part of molecules that carry information. Ribose, specifically, is tied to RNA in living systems on our planet. So when scientists report ribose and other sugars in Bennu material, they are not merely adding another item to a catalog. They are asking whether some of the molecular parts later used by biology could have been made, preserved, or delivered by non-living processes in the early solar system. That question is more useful than the myth. A skeleton would be a spectacle. It would demand a rewrite of human history, planetary history, and the timeline of life itself. It would also require evidence of a kind no Bennu study has provided. But sugars in asteroid material do something different. They give scientists a testable path. They invite comparison between meteorites, returned samples, laboratory chemistry, and models of the young solar system. They help researchers ask how raw ingredients could have formed in water-altered environments, how they could have survived inside carbon-rich bodies, and how they might have been distributed across young worlds. This is where the earlier brine story returns with new force. Bennu's material carries evidence connected to water alteration. Smithsonian-led work described signs that evaporated water left briny salt minerals in the material. Those salts, including sodium-rich minerals along with carbonates, sulfates, chlorides, and fluorides, point toward environments where liquid water once interacted with rock on Bennu's parent body. Not an ocean on Bennu as it exists now. Not a living habitat, but an ancient chemical setting where water, salts, minerals, and organic molecules could meet. In that setting, sugars become part of a broader question. How do simple organic molecules assemble, change, degrade, or persist when they are exposed to minerals and brines? How do water-altered rocks affect organic chemistry? Which ingredients can form without life, and which arrangements require biology? Bennu does not answer all of that at once. It cannot. But it gives scientists a rare, clean sample from an asteroid, one collected directly from the surface at Nightingale during the touch-and-go maneuver on October 20, 2020, then sealed for return to Earth. That protected chain matters because sugars and other organics are also found on Earth. Contamination is always a concern in astromaterials science. The power of OSIRIS-REx is not that it made interpretation easy, but that it made the evidence stronger. A returned sample handled through NASA's curation systems allows researchers to study ancient material with context and care. It lets them examine what is present, how it is distributed, and how it relates to minerals in the same grains. The temptation, again, is to let familiar molecules do too much work. Ribose feels close to RNA, and RNA feels close to life, and life feels close to bodies. But that chain of association is not a chain of evidence. Chemistry can approach biology without becoming biology. A molecule can be part of living systems on Earth and still form in places where nothing is alive. Amino acids can exist without proteins. Nucleobases can exist without genes. Sugars can exist without cells. This is not a downgrade. It is the discovery. The universe does not need to hide a human skeleton inside Bennu to be astonishing. It is enough that a dark, carbon-rich asteroid can carry water-altered minerals, salts, amino acids, nucleobases, and sugars from the deep history of the solar system. It is enough that the same families of molecules life later used may have been available in non-living environments before Earth became a biological world. That does not tell us that life is easy. It does not tell us that life is inevitable. It does not tell us that Bennu was alive. What it does is sharpen the starting conditions. It helps scientists move from imagination to experiment. If these ingredients were present in ancient asteroid material, then early Earth may not have had to make all of them alone. Some could have been delivered. Some could have been shared among worlds and small bodies. Some could have circulated through the young solar system as chemistry, long before they became biology anywhere. That is the more precise version of wonder. The myth wants Bennu to contain a finished story, a person, a death, a secret civilization, a violation of time. The evidence gives us something earlier and more open. It gives us ingredients before recipes, letters before messages, sugars before cells. Not a creature preserved in stone, but a chemical landscape in which the raw materials of life can be studied before life enters the frame. And beneath even that chemistry, the timeline goes deeper still. Because part of Bennu's strangeness is not only what molecules it carries, but where some of its dust may have come from. The asteroid belongs to solar system history, but NASA has also reported stardust and interstellar organic material in its samples. That means the archive may contain grains older than the sun itself, fragments from before the planets formed, older than Earth in the only precise sense this story allows. Not bones older than Earth. Dust. Chemistry. Ancient material from the dark before our world. That ancient material from the dark before our world is where the Bennu story becomes most delicate, not because it proves the rumor, because it explains why the rumor was able to borrow one true idea and twist it into something impossible. There is a real sense in which part of the Bennu sample can be described as older than Earth. NASA has reported stardust and interstellar organic material in the returned Bennu samples. That does not mean the asteroid is a coffin from before humanity. It does not mean a body was sealed inside rock before our planet formed. It means that inside the carbonaceous material delivered by OSIRIS-REx, scientists can find grains or components whose history reaches back beyond the birth of the solar system. This is the strange, precise version of the story. Bennu itself belongs to solar system history. It is part of the long chain of material that formed, changed, broke apart, and traveled through the same planetary neighborhood that produced Earth, Mars, the Moon, and the rest of the worlds orbiting the Sun. NASA describes the Bennu sample in a roughly 4.5 billion year early solar system context. That is already almost beyond ordinary imagination. But within that archive, some tiny pieces may have an even deeper origin. They may be presolar grains, dust made around earlier stars, scattered into interstellar space, then swept into the cloud of material from which the sun and planets formed. To hold that idea clearly, we have to separate two timelines. One is the timeline of rock, dust, ice, minerals, and organic chemistry. This timeline reaches into the formation of the solar system and, in the case of pre-solar material, even before it. It includes particles born from ancient stellar environments, materials traveling through interstellar space, and compounds that became trapped in the bodies that later moved around the young sun. The other is the timeline of humans. Those timelines are not close. They are not even separated by a dramatic gap that can be bridged by a hidden chamber or a lost civilization. They belong to different scales of reality. Dust can be older than the sun. Human bones cannot. That is why the real discovery is more fascinating than the fake skeleton claim. The false version imagines something visually shocking, but scientifically incoherent, a human body where humans could not have existed. The real version asks us to imagine something smaller, quieter, and much older, microscopic grains that survived the violence of cosmic recycling, carried forward into a near-Earth asteroid, returned to Earth inside a sealed capsule, and opened under careful laboratory conditions at NASA Johnson Space Center in Houston, Texas. The difference matters. A skeleton would be a biological structure. It would imply an organism with anatomy, development, heredity, and an evolutionary history. A human skeleton would imply Homo sapiens, a species with a very recent place in the history of Earth. It would also imply the entire chain of conditions required for humans to exist, a planet with oceans and continents, biological evolution over immense time, primates, hominins, and finally, modern humans. None of that belongs to the pre-solar or early solar system dust record. A pre-solar grain is something else entirely. It is not a fossil. It is not a cell. It is not a message. It is not evidence of a mind. It is a tiny mineral or material component with a chemical and isotopic story that can point beyond the solar system. It belongs to the physics and chemistry of stars, molecular clouds, and planetary formation. In a cinematic version of this investigation, it is not a bone in a tomb. It is a speck of night that arrived before the sun became the center of our sky. That is the kind of ancientness Bennu can offer. When OSIRIS-REx brought back 121.6 grams of material from asteroid 101955 Bennu, the value of that sample was not in its size. It was in its condition, its context, and its origin. The capsule that landed at the Department of Defense Utah Test and Training Range on September 24, 2023, carried material collected directly from the asteroid's surface by the touch-and-go sample acquisition mechanism. Once that material was protected and curated, scientists could examine details that no telescope could resolve from afar. Inside that material, NASA and collaborating researchers have reported carbon-rich chemistry, hydrated minerals, salts connected to ancient brines, amino acids, nucleobases, sugars, stardust, and interstellar organic material. The pattern is not a body. It is a record. It is a collection of clues about how complex chemistry can be assembled, preserved, altered by water, and carried through space. The stardust part of that record changes the emotional scale of the story. We are used to thinking of asteroids as old. They look like leftover worlds, fragments that escaped becoming planets. Bennu is often described in that spirit as an archive from the beginning of the solar system. But presolar grains push the mind one layer deeper. They suggest that some material in the archive was not merely present when Earth formed. It had already existed before Earth was possible, before the planets, before Bennu's parent body, before the sun. This is not fantasy. It is the sober implication of ancient dust surviving inside primitive solar system material. And it is exactly why language has to be handled carefully. If someone says Bennu is older than Earth, that can blur the truth. Bennu and its parent material are tied to the solar system's formation roughly 4.5 billion years ago in context. Earth also formed in that same broad era. The sharper statement is this: Bennu samples can contain components including stardust or interstellar organic material that predate the solar system. The asteroid is not a time capsule containing impossible humans. It is a solar system body that can preserve some ingredients inherited from before the solar system existed. That distinction is not a technical footnote. It is the difference between science and myth. The fake skeleton story takes the feeling of deep time and attaches it to the wrong object. It uses the phrase older than Earth as if age alone could make any scene possible. But age does not erase sequence. A human body cannot appear before the evolutionary pathway that produced humans. A skeleton cannot precede the planet on which its species evolved. Bones belong to biology. Biology belongs to environments and histories. Human biology belongs to a tiny final sliver of Earth's timeline. Dust does not face the same limit. Dust can be inherited. Dust can drift between stars. Dust can be incorporated into new systems. Dust can survive as a trace of environments that disappeared long before Earth had a crust, long before oceans formed, long before any cell on our planet divided, long before anything like a skeleton existed. That is why the Bennu sample is not less interesting without a skeleton. It is more interesting because it forces us to think beyond familiar shapes. A skeleton is immediately recognizable. It turns the universe into a human-centered mystery. But the presolar grains do the opposite. They move the human story out of the center. They remind us that the materials of our solar system were not created in isolation. The cloud that formed the sun was not a blank beginning. It contained inherited matter, including material from older cosmic environments. In that sense, Bennu is not only an archive of the early solar system. It is a place where earlier archives were folded into a new one, layer upon layer. Stardust before the sun. Solar system chemistry before Earth became the world we know. Water-altered minerals and salts from Bennu's parent body. Organic molecules that resemble ingredients used by life on Earth, but do not amount to life. And finally, a modern spacecraft from Cape Canaveral, Florida, reaching out across millions of miles, touching the surface at Nightingale, and bringing a portion of that archive home. The route from ancient stars to a clean room in Houston is stranger than the skeleton rumor because it is real. It does not need a hidden chamber. It does not need an alien corpse. It only needs the universe to behave the way planetary science already shows it can behave, making elements in stars, scattering grains through space, forming new systems from old material, and preserving some of that inheritance inside small dark bodies. This is the quiet science fiction of Bennu. Not a person trapped in an asteroid carrying traces of worlds before worlds. But once the phrase older than Earth enters the story, the human claim has to be brought back into focus. Because if dust can be older than the sun, it becomes even more important to ask what cannot be. A grain can cross that boundary. A molecule can belong to an ancient chemical inheritance. A human skeleton cannot. To see why, the scale has to shift from stardust to fossils, from the birth of the solar system to the much younger record of our own species. From stardust, the story turns toward bone. Not because Bennu contained bone, and not because any laboratory result has pointed toward a body hidden in asteroid rock. It turns there because the rumor depends on a collision between two very different clocks. One clock belongs to the early solar system, to carbonaceous material, hydrated minerals, salts, organics, and grains that may carry an inheritance older than the planets. The other belongs to us, to primates, to anatomy, to fossils, to the brief and fragile record of Homo sapiens on Earth. Those clocks do not overlap in the way the viral story needs them to. Bennu's scientific power comes from its ancient context. NASA describes the Bennu sample as roughly 4.5 billion years old in the sense that it preserves material from the early solar system. That phrase matters. It does not mean Bennu is a museum display with familiar objects placed inside it at random. It means the asteroid and its parent material are part of a very old chemical archive, a record of processes that were happening when the planets were forming, when Earth itself was young, and when the ingredients of later worlds were still being sorted, heated, altered by water, broken apart, and preserved. That is the scale of Bennu. Now place the human claim beside it. The Smithsonian Human Origins Program states that fossils from Jebel Irhoud, Morocco, dating to about 300,000 years ago, are among the oldest known Homo sapiens fossils. That number is immense when we imagine individual lives, generations, migrations, climates, and vanished landscapes. 300,000 years is older than cities, older than agriculture, older than writing, older than every civilization whose ruins can still be walked through today. But against Bennu's early solar system context, it is almost the last flicker of the clock. A human skeleton described as older than Earth is not a difficult claim waiting for laboratory confirmation. It is a claim that fails at the first comparison. It fails before microscopy. It fails before isotope work. It fails before anyone has to ask whether a bone surface shows mineral replacement, whether collagen survived, whether the specimen was contaminated, whether the sample was exposed, or whether a clean room protocol was broken. It fails because the biological lineage required to make a human skeleton is far too young. Homo sapiens are not 4.5 billion years old. Human bones are not older than Earth. The species capable of leaving a human skeleton belongs to a much later chapter of planetary history. This is the reality check that the rumor tries to avoid. It uses the phrase older than Earth as atmosphere. It lets that phrase become fog. In the fog, an asteroid becomes a tomb, chemistry becomes remains, and ancient dust becomes a person. But science has to separate what sounds ancient from what can actually be ancient. A presolar grain can be older than Earth. A component inherited from interstellar material can be older than Earth. Some chemical ingredients inside a carbonaceous asteroid can connect us to conditions before Earth became the living planet we know. But a human skeleton cannot be placed inside that category without breaking the entire history of life. This is not a small correction. It is the central contradiction. The rumor asks us to imagine a human body sealed inside a record from a time when humans did not exist, when mammals did not exist, when the entire later story of terrestrial evolution had not yet unfolded. It asks us to compress billions of years into a single impossible image. It takes the grandeur of deep time and turns it into a prop. And yet, deep time is already strange enough. The real Bennu material, returned by OSIRIS-REx and curated for study at NASA Johnson Space Center in Houston, Texas, is not ordinary stone in the everyday sense. It contains high carbon content and evidence of water-bearing minerals. Later reporting described hydrated minerals, clay minerals, sodium-rich salts, carbonates, sulfates, chlorides, fluorides, amino acids, amines, formaldehyde, carboxylic acids, polycyclic aromatic hydrocarbons, N-heterocycles, nucleobases, sugars, and pre-solar components. That list is not a body plan. It is not a skeleton. It is not anatomy. It is chemistry, mineral history, and cosmic inheritance. The distinction is quiet, but it is everything. A skeleton is organized biological structure. It belongs to an organism. It implies development, tissue, physiology, ancestry, and a life that once moved through an environment. A human skeleton implies the evolutionary history of humans, the emergence of our species, and the planet that shaped us. It cannot be detached from Earth's biological timeline and placed billions of years earlier without evidence of a kind that would overturn not just one interpretation, but the entire framework of human origins. No such evidence exists in the Bennu story. The actual evidence points somewhere else. It points toward prebiotic chemistry, toward environments where water and salts may have helped molecules interact, toward organic compounds associated with biology on Earth, but not exclusive proof of biology beyond Earth. It points toward the question of how widely the raw materials of life may have been distributed before life existed here. That is not a diminished story. It is a more disciplined and more powerful one. The Smithsonian comparison helps keep the scale honest. Jebel Irhoud, Morocco, gives us a human anchor, about 300,000 years for some of the oldest known Homo sapiens fossils discussed by the Smithsonian Human Origins Program. Bennu gives us a solar system anchor, roughly 4.5 billion years in early solar system context. Between those two numbers lies a gulf so wide that the false headline cannot cross it. To feel that gulf, imagine time not as a chart, but as a corridor. At one far end is the formation of the solar system, with dust, ice, metal, rock, carbon compounds, and the small bodies that would preserve ancient chemical records. In that darkness, Bennu's parent material belongs. Water alters minerals. Brines leave salts. Organic molecules form, survive, or are delivered. Some grains may carry histories from before the sun. Much, much later, Earth becomes a world with a long biological record. Life changes the atmosphere. Continents shift, oceans open and close, extinctions erase entire branches, and evolution continues its slow work. Only near the very recent end of that corridor do Homo sapiens appear. The fossils from Jebel Irhoud sit in that late human zone, astonishingly old by human standards, but not remotely close to the age of Bennu's ancient material. The rumor erases the corridor. Science restores it. That restoration matters because misinformation often works by stealing one legitimate phrase and attaching it to an impossible conclusion. Older Than Earth has a real place in this story when we are talking carefully about pre-solar grains or ancient components preserved in asteroid material. It becomes false when it is used to describe a human skeleton. The words did not become dramatic because they were wrong. They became dangerous because they were close enough to something true to sound plausible. The remedy is not to drain the story of wonder. The remedy is to place the wonder where the evidence actually is. There was no need for NASA to find a body for Bennu to matter. The OSIRIS-REx sample already brought Earth a rare archive, material from a near-Earth asteroid, protected through return, handled for laboratory analysis, and rich with clues about early solar system chemistry. The awe is not in a hidden corpse. It is in the possibility that before Earth was alive, some of the ingredients later used by life were already being made, moved, altered, and stored in small dark worlds. That is stranger than the rumor in a quieter way. A skeleton would be a closed answer, a sensational object demanding an impossible past. Bennu's real material is an open question. It does not say that life existed there. It does not say that humans came before Earth. It does not turn asteroid dust into a fossil record. It asks how chemistry became so widely available, how water-shaped minerals and salts interacted with organic molecules, and how much of Earth's later biological potential may have been assembled from ingredients that were already traveling through space. So the human timeline does not weaken the Bennu discovery. It protects it. By saying no to the impossible skeleton, the timeline lets the real signal come through. Homo sapiens belong to hundreds of thousands of years, not billions. Bennu belongs to the early solar system. Presolar grains may reach even deeper into cosmic history. These are different layers of time, and their differences are what make the story intelligible. The false headline collapses them into one image. The evidence separates them again. And once they are separated, the final shape of the story becomes clearer. NASA did not return bones, fossils, aliens, or human remains from Bennu. It returned a small amount of carbon-rich asteroid material, carrying water-altered minerals, salts, amino acids, nucleobases, sugars, and ancient components that may help scientists study what was present before Earth became alive. Not a skeleton older than Earth. A cosmic signal from before life asking how far life's ingredients had already traveled. That is where the real ending begins, not with a corpse hidden in stone, but with a question carried in dust. By the time the Bennu sample reached the laboratories at NASA Johnson Space Center in Houston, Texas, the false image had already done what false images do. It had made the story smaller by making it louder. A skeleton inside an asteroid sounds enormous for a moment, almost mythic, as if human history had secretly begun before Earth itself. But under scientific light, that image cannot survive. Bones belong to biology. Human bones belong to a species whose deep fossil record reaches back hundreds of thousands of years, not billions. Bennu belongs to the chemistry of the early solar system. These timelines do not overlap in the way the rumor needs them to. And yet, after the rumor falls away, something stranger remains. The sample was not empty of meaning. It was not just dust in a container. OSIRIS-REx delivered 121.6 grams of material from asteroid 101955 Bennu, and that material has become a kind of quiet signal from a time before Earth was alive. Not a signal in the science fiction sense of a deliberate message. Not a transmission from intelligence. Not a code arranged by unknown hands. A signal in the older, scientific sense. A physical trace, a pattern in matter, a record that can be read only by careful instruments and patient comparison. The capsule that landed on September 24, 2023, at the Department of Defense Utah Test and Training Range did not carry a body. It carried carbon-rich asteroid material, protected from ordinary Earth exposure, returned by the first United States mission to deliver a sample of an asteroid to our planet. That protection matters because the question was never whether Bennu could shock us with an impossible artifact. The question was whether a clean sample could help scientists see what kinds of chemistry were available in the young solar system, before life on Earth took hold and before Earth's active geology erased so much of its own earliest record. That is the difference between a hoax and a discovery. A hoax asks us to ignore scale, contamination, dating, biology, and context. A discovery survives those things. It becomes more interesting because of them. NASA's early analysis reported high carbon content and evidence of water-bearing minerals. Later work described hydrated minerals, clay minerals, sodium-rich salts, carbonates, sulfates, chlorides, and fluorides. Smithsonian-led research connected some of that mineral story to evaporated brines, suggesting that Bennu's parent body once held environments where salty liquid water could alter rock and concentrate ingredients. Again, this is not life. It is not a cell. It is not a fossil. But it is a setting where chemistry could change, gather, and react. That distinction is the heart of the episode. The Bennu sample contains life-related chemistry, not life. It contains amino acids, including 14 of the 20 used by life on Earth to make proteins. It contains all 5 nucleobases used by terrestrial life to store and transmit genetic information in DNA and RNA: adenine, guanine, cytosine, thymine, and uracil. It contains sugars, including ribose and other related molecules, as described in NASA reporting. It contains organic categories such as amines, formaldehyde, carboxylic acids, polycyclic aromatic hydrocarbons, and N-heterocycles. These names are not as instantly cinematic as a skeleton. They do not give the eye a shape to hold on to. But they are more consequential because they belong to a real chain of evidence. They show that some of the molecular ingredients associated with life on Earth can exist in ancient asteroid material without requiring biology to make them. That is the cosmic signal. It says that before life was a forest, before it was a cell, before it was a strand of inherited information inside living tissue, some of its ingredients may have already been moving through the solar system in stone, ice, dust, and altered minerals. They were not alive. They were not trying to become alive. Chemistry has no plan in that sense. But the presence of these molecules in Bennu material helps scientists ask how widespread the raw materials of life may have been before Earth became the planet we know. That question is powerful because it does not need exaggeration. If amino acids can be found in a carbonaceous asteroid sample, we do not need to invent bones. If nucleobases can be detected in returned material from Bennu, we do not need to invent a message. If salts and water-altered minerals can point back to ancient brines, we do not need to invent oceans full of alien creatures. The real story is not that Bennu was inhabited. The real story is that Bennu may preserve evidence of chemical environments where some of the same classes of molecules used by living systems on Earth were already present, long before there were humans to give them names. And the scale of that is almost harder to absorb than the fake claim. A human skeleton would have narrowed the mystery to one impossible object. The Bennu sample opens the mystery outward. It connects Cape Canaveral, Florida, where OSIRIS-REx launched on September 8, 2016, to a near-Earth asteroid roughly 1,600 feet across. It connects the touch-and-go moment at Nightingale on October 20, 2020, to cleanroom curation in Houston. It connects NASA Goddard Space Flight Center, the University of Arizona, NASA Johnson Space Center, the Smithsonian National Museum of Natural History, and other scientific collaborators to a shared act of reading matter older than memory. And it connects Earth to a larger chemical neighborhood. Not every asteroid is Bennu. Not every world preserves the same conditions. Not every organic molecule leads toward biology. The presence of ingredients is not the same as a recipe completing itself. Life is not explained by naming amino acids, nucleobases, sugars, salts, and water-altered minerals. But those ingredients matter because they mark the boundary between an empty universe and a chemically generous one. That is the unresolved edge the sample leaves us with. Before Earth became alive, how much of life's inventory was already scattered around it? How much came from local chemistry on the young planet, and how much was delivered, shared, or preserved by asteroids and other small bodies? Were these molecules rare accidents, or were they part of a wider chemical background that many young worlds inherited? Bennu does not answer all of that. 121.6 grams cannot speak for the entire solar system, but it gives scientists a clean, physical archive to test against those questions. In that sense, the final correction to the viral headline is not simply, NASA did not find a skeleton. That part is true, but it is only the first door closing. The more important correction is that NASA found something that belongs to a deeper and more legitimate mystery: carbon-rich material, water-altered minerals, salts, amino acids, nucleobases, sugars, and ancient components from a small asteroid whose history reaches back toward the formation of worlds. No bones, no fossils, no aliens, no human remains. Only grams of dark material, carried home across space, opened under human care, and studied for traces of chemistry that may have preceded biology itself. The false headline wanted Bennu to be a tomb. The evidence makes it an archive. And an archive does not need to contain a body to change how we understand our origins. Sometimes it contains dust, sometimes salts, sometimes molecules whose names sound ordinary only because science has learned to pronounce them. Sometimes the most unsettling message from space is not that someone was there before us. It is that, before there was anyone, the ingredients were already traveling.